بسم الله الرحمن الرحيم، وعلى بركة الله نبدأ فعاليات اليوم الثاني. Arc flash generally refers to the dangerous exposure to thermal energy released by an arcing fault on an electrical power system. And in recent years, arc flash hazards have become a prominent safety issue in many industries. This safety toolbox will discuss the hazard of arc flash, new standard on electrical safety and arc flash, prevention and protection. This presentation arc flash hazard will be presented by Engineer Ubaid Ali Rashid. Engineer Ubaid Ali Rashid is a lead electrical engineer in the consultant section of Sadara Chemical Company. He has an executive master in business administration. He is a member in IEEE committee, ASME committee, and Prince Mohammed bin Fahad University master program. Engineer Ubaid, you can start.
بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. صباح الخير جميعا. First of all, I would say good morning, gentlemen. I'm really happy to be with you this morning, and we will start our meeting or our gathering with the safety as my colleague introduced for it. We'll start with the why it's a concern. The IEEE and another standards in the national in United States, they start since 15 years when they saw the accidents increase with the flash and electrical system. So they make a survey and they found really it is a risk and really it is a concern. So for sure here in Saudi Arabia, a lot of companies looking for the same concern. So we're going to discuss today what is the issue and what is the cause and how we can prevent our guys, which is they are exposed to these risks. So this is the presentation, and what is the purpose of this presentation? We're going to talk about introduction, just a small introduction for it, and also we're going to talk about the new standards which is established on the standard NAC and the arc flash also prevention and protection. Also, we're going to discover 4 main topics. The first one, the introduction, which is we talk about it, and the arc flash injuries, and also protective clothes and equipment and prevention. So what is the arc flash? Why it is a hazard? It is a dangerous condition that associated with the release of the energy caused by electrical arc. So as an engineer, we know this arc is an energy. So there is a formula we study. This energy can increase and decrease by 2 factors, which is, you see it in the power, our electrical power, this is one factor. Second one, the time, that time which is exposed to this risk. So if we reduce these 2 factors, we're going to reduce the energy. If we increase these 2 factors, we're going to increase the energy. So this is very important for engineers to look at it to prevent this risk. What is the arc? What is the arc concerning us? It is a short circuit, actually. Simply, it's a short circuit flowing in the air. So this is the dangerous which is exposed to the people. The characteristic of the electrical arc, just to make sure it is understood very well. The arc will escalate it, and if it's not controlled, it will be escalated as per the energy. So if we don't control it, it will go, it will flow. So it can catch anybody, it's not working, maybe the guy, he is not involved in the job. So this is the risk also for this condition. So the single phase electrical can also engulf a second, third conductor in only 2 cycles. It's very fast. You cannot think even about it. So it's very fast. So if there is anything, you cannot escape. You cannot try to do anything. So it is very, very fast. It's only 2 cycles, which is very, very fast. So the electrical arcs also current propels the arc away. It's pushing the arc everywhere. So we will see when maybe in the end of the presentation, we will see a video. It's not important to have a problem with the guy he's working inside the cubicle, but it might be also the guys he's sitting far away about this problem. So this is the issue with these arcs. So electrical arcs also, and the blast produced dangerous with the 3 main concern or 3 main risk, which is the pressure waves, which can push the human being out of the source, and also the sound. Sound is very huge sound. It can damage also the hearing. And also, this is concern and still under discussion till now, which is the molten steel flying away. So I can wear the clothes which can protect me against the heat and the arc, but there are small particles coming out from this source. So this is very, very dangerous. It can even cut the metal, not only the body of the human. So this is very important, and also it is under discussion how to prevent it. So till now, still there is no issue, no solution, no final solution of this. So why this happen? It happens for two main, you can say, two main reason. One of them, the environment. What is our environment? So it can be dust, it can be corrosion, it can be animals coming inside the electrical system if it's not insulated very well, especially for the remote area, which is in the desert or in the it's not in the substation, which is very close. Animals can get in and can make short circuit. And also by accidental touching. If somebody is working near to energized circuit or energized bus, by mistake he can touch something which is he doesn't know about it. So this one also can make an big arc for this. Dropping tools also, it's again for a human being. And BD, which is partial discharge. If we don't maintain our system, it can have partial discharge, which is, it can damage the insulation and it can reach up to the body of the switchgear or the MCC and can make the flashover. Also, a failure of the insulation materials, which is talking about the age of the equipment. So people expecting the electrical equipment can run for the whole years, which is not right. It has an age. Each equipment has an age. So after this age, we should do a maintenance or repair or modification. So this is very important. So the last point, which is here, is the equipment failure. Also, the equipment failure, it can happen if we don't also do good maintenance for it. So this is very important to associate with this arc flash. The NFPA made a survey, which is good survey, who is the affected companies or business with this problem. and which section is more affected. So you're going to see the left survey, which is which business is exposing to these risks. So we're talking about our companies, like electricity company. I think it's falling under professional and business services, which is the left side of the survey. It's number 2. If you see the first one, we are not construction companies, and this is by the way, this is for the fatalities. And we are not first company, and we are falling under the professional and business services, which is 258. This is only in the United States during 10 years. This is fatality because of this risk. I'm not scaring people here, but I'm saying this is really a risk. We have to take care about it. If we're talking about the right survey, which is which section from the company, like maintenance, engineering, a lot of section on the company, who is the more exposed to this risk? So we're talking the first one, which is the contractor. We bring third party to do job for us, and they maybe shortcut or do something which is overconfident. They might lead to this risk. Also talking about installation and maintenance and so on and so forth. So maybe you observe something which is strange here, which is the last point, management. Management, what they have to do with the risk. I mean, they are working, no, they are not working, but they are not providing the right equipment. They are not alerting their people. They are forcing people sometimes to do it because there is a top force, maybe from the senior management or from the government. You need to do this. Okay, I will do it if it's safe, but if it can lead my people or my colleague to risk, or I can say as a management, as a decision making, I said no, it is not safe to do it, so let us do it in right way so we can prevent. So management, they are involved in this fatalities. So this is some standards. OSHA, what they are saying. Life equipment or life parts and parts that an employee may be exposed should be de-energized. So most of the important thing, people should not work in energized system. So they have to de-energize it and lock it out and tag it. If we don't do this, or we are forced to do this energized, I mean, we cannot isolate it, and we can work energized. So at least we need to do some mitigation too. So we're talking about another standard, which is this is a new standard. Some companies is doing it, and some companies not doing it, which is the employee working in an area where potential electrical hazard existing shall be provided with the shall use personal protective equipment. So any equipment which is required to do any maintenance, so they will be assigned. Nobody will work here unless he is full wearing these clothes. So this is another standard. A flash hazard analysis shall be done before personal approach any exposed electrical conductor and circuit. So this is also a very important standard, and all companies should comply with this. This is a new system. We are using it in our company. I don't know about the SEC or another companies, which is we design our switch gears or equipment with maintenance switch, which is if we need to work on it, we have to put the switch to maintenance. So if there is any problem happen, we come back to the second slide, which is time. So this one it will do with the protection relays, so it will minimize the time in case if there is something happen. It will not be big energy, so at least we are protected. So this is, by the way, it's a standard. This is the damage of the arcs, and what we can have out of this. We can have a very big noise, explosion, vibration, and the thermal radiation. Arc injuries. The arc shock severe burns, and it can also do the blindness. The blast, which is the explosion, happen out of the short circuit also. Shrapnel materials, which is, we will talk, I talk already about it, and still it's not 100% solved, because if you wear the flash suit, still the small particles, if it's exposed to this, it can hit your body, even though it can hit even the metals. Also the pressure waves we're talking about, it can push the guy and it can hit the wall, or it can hit any sharp edges around him. This is the factors which is affect on the severity of the arc. The power, which is talked about it in the slide. Distance also. There is a design system based on the calculation, which is, it's done on the design stage, how distance you need to stay along with the sources, or what is the arc if it's happened, how long it can transfer. This is the distance. Time also, we're talking about it. If we reduce the time, and the new standard now talking about this maintenance switch, you have to install it in your MCC, which is, if there is no arc resistance MCC, you need to do. In case of the maintenance guys, they are doing, they have to put the switch in maintenance, so it will reduce the time in case if there is any problem. So this is very important. It's a standard. See the sign of the sharpness. This is the metal which can fly out of the short circuit. It can hit even the metal, so it's like a bullet, really. So the clothes, it will not protect this, but the NEC and another standard companies, they are working how we can prevent this. They just picture how we can image the sound coming out of this sorry, out of this flashover. So it is more than the turbine of the airplane. If you just go and put your air on the near to the sorry, near to the turbine of the airplane or any turbine, so it is more high than that. Pressure wave injuries, what can do? The arc blast can throw a worker out of his place. Just if we know about the pressure, how the pressure is strong, see the pressure coming out is an average out of the flashover. It's 2,000 IPS feet square, which is, it is very high. Talking about bars, like 40 bars or something. It's very, 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 very high. So how we can measure the heat of the arc flash? There is a unit, they call it calories. What is the calories? The calories is the amount of heat needed to raise the temperature of 1 gram of water by 1 degree centigrade. So this is the calories. Thermal energy is measured in calories per centimeters square. So let us see what is the heat. If we give I just put here as an example, what is the heat we are exposed to. If we get 1.2 calories, it's like you are holding a lighter flame for 1 second. So any system here, we never see as industrial, we never see calories less than 4. So we're talking about minimum 4 calories coming out from the system till 40, 50 and above. So if you're talking about 1.2, like you are holding a lighter for 1 second, and you calculate it, multiply by 4, which is the minimum calories we can get from any system. So I don't think so. It's a painful. So this is the amount of the heat we are exposing to. So this is the categories we are categorized, or the standard categorize the flashover. The 0, 1, 2, 3, 4, which is we can wear the protection clothes to protect us from this heat. So 4 calories, this is the minimum which we're talking about, and 8 calories, and 25 calories, and 40, and there is companies, they are not allowing to design their system if the short circuit it's more than 40. Like in Sadara, our companies, and in Aramco, we are not allowing to design system more than 40. If it's 40, do something for me. I will not let my people working in this system. So I don't know, some companies they are allowed, but we are concerning about this. So this is the type of the clothes we are wearing, or we provided to our guys to work on any MCCs or any energized circuits. So flame resistance, this is a clothes, it's designed to tolerate the heat and the flash. So in case if there is a flash over, it will not burn. So it will protect at least the people who they are working there. So we are protecting also the people from the light which is coming out of the flashover. The task with the potential of arc flash. So opening a switch. This is some exercise they are doing when they get the flashover, and inserting or removing the circuit breaker. This is some activities the technician or the engineers doing this. It might be a risk for them. So arc flash hazard analysis. If your work must be done or near energized electrical equipment, identify the potential. This is very important, gentlemen. We have to identify the risk. We have to tell the guys, you have to take a permit. What is the risk? What is the mitigation? So there is no zero risk. So if there is a good analysis for the job, we can prevent a lot of accident. So also this, we are putting as a standard, this is also being asked by standard, NEC, to put this in any switchgear on any board that can cause a flashover. There is some information here. What is the boundary? What is the flash? If it's a fly, how long it takes? This is there. And you're talking about the incident energy, calories, we talk about it. And we're talking about the working distance. It's 24. See, 24 inch. You cannot work out 24 inch. So you need to do something. You need to wear something which can protect you. So this is standard. We have to stick it on to alert our people. There is a risk. So we're gonna see videos to just show what is the arc and what it can do for people working on. So we're gonna see the first video. Maybe to prepare the video. You can see here, this guy is working in system.
You have
this is the flashover.
Now, one of the most dangerous myths in our business is that 100% cotton is an upgrade.
So
over
he is
polycotton.
not wearing
It doesn't
a
ignite in dark.
protection
Well, clearly it
clothes.
does. Cotton ignites just as easily, it burns hotter, it's harder to extinguish, and it's typically heavier than synthetic cotton blends, meaning there's more fuel for a longer fire. And you can see in this instance how very rapidly the fire has spread to the entire back of the garment. Stop, drop, and roll will not put this fire out. It is entirely too aggressive a fire to be put out like that. You're going to need an extinguisher to put this out.
It's a little windier this time.
Here we are in slow motion. You get a very good look at the arc. Again, you have projection of the arc significantly out of the box, 3-4 feet away, a large amount of molten metal, and the garment essentially instantly on fire.
This is only for 80 system, for 80 voltage.
Frame by frame gives us another terrific look at this arc, and you can see how rapidly the entire mannequin is gone. He's invisible. He's completely enveloped in this arc. The molten metal, the arc flash itself are 2 or 3 feet at least, and perhaps more, out of that box.
So we can see another video, and it shows that wearing the clothes, which is protecting against the flashover. So we can see here, same flashover, but he's wearing a protection equipment.
Fire on the garment after the arc is over. The flame-resistant clothing did its job. In slow motion, you have a very good look here. The arc comes out of the box, wraps around to the left of the mannequin and around his back. A large amount of molten metal is thrown out as well. But once again, when the arc event is over, there is no fire on the garment. The frame by frame will give us another look at the arc. You can see it come out of the box, up the face and chest of the mannequin, and around to the left as well, and around the back. Arcs do unpredictable things. This one was at least 4 feet out of the arc gap.
So it's very big different. So now we need to see how is the flashover is transferring. It's not only against the guy who's working inside the cubicle. It can goes also far away. So let us see this video.
This is a 30 amp disconnect, a category 1 arc, and it does something very surprising. The hazard was not directly in front of this box. The arc, as you're going to see very clearly in slow motion, leaves the box and travels down the bus bar at the bottom of the sled and blows a hole in the ultra-soft fabric wall at the back. Look at that. So NFPA 70E talks about working near energized electrical equipment. This is a clear example of the hazards even 15 or 20 feet away. The arc did not come out of the box. It traveled down the bus bar and blew a hole in the rear wall. You can clearly see in the frame by frame the same phenomenon.
So it's a fly away. It's not direct fall. So if somebody is working there or sitting there, it will catch him. Okay, we summarize now for the presentation. So I think two important things we have to do. The distance, we have to respect the distance, and we have to make sure our guys, they are wearing the right equipment and right clothes during any job which is inside the electrical system. Sorry. Reduce the fault learning time, which is, we talk about it in the first, we have to make sure something which is reducing the time of protection, reduce the short circuit current also, improve the equipment maintenance, this is very important also, increase the working distance. We have to make sure distance is very clear and very enough for guys to work, increase or reduce the energy exposed, and conduct predict safety audit. This is very important. We need management to go outside and see it's risk or not risk. So this is very important. We need to do safety audit on our systems. Also, there is a system which is hanged door instead of bolt, this is in the design actually. And work de-energize as possible as you can. Try to work de-energize. So this is what I have. I hope it can add value for you. And if you have any question, please, I think we have 1 minute. Any question? Thank you very much.
نشكر المهندس عبيد الرشيد. فليتفضل الأستاذ عبد الرحمن العبيد لتكريم المهندس عبيد الرشيد. أيها الإخوة الحضور، الجلسة الرابعة في محور الطاقة المتجددة يترأسها المهندس عبد الرحيم الشيخ، مدير مشروع محطة توليد ضبا الخضراء ومشروع محطة توليد رابغ. ستبدأ الجلسة 9:15.
صباحكم بالخير. تبدأ الآن جلسة الطاقة المتجددة، والتي يرأسها المهندس عبد الرحيم الشيخ، مدير إدارة مشاريع التوليد بالغربية والجنوبية بالنيابة، ومدير مشروعي رابغ وطيبة.
السلام عليكم ورحمة الله وبركاته. الحمد لله والصلاة والسلام على أشرف المرسلين. الحمد لله رب العالمين والصلاة والسلام على أشرف المرسلين سيدنا محمد. In beginning, I would like to thank Training Center from Saudi Electricity Company to prepare and organize for this forum. Today, we have 4 sessions regarding one of the major topics related to the renewable energy. In beginning, on this table there is professors and expert people to explain, to present 4 subjects of the major subject for the renewable energy. Professor, the first sessions, it will be related to the photovoltaic solar energy. It is presented by Professors Omar Badran. Omar Badran is a professor at Faculty of Engineering, Taiba University, PhD in Mechanical Engineering from Bradford University, UK. He won several awards due to his academic excellence. Please, Professor, start.
Thank you very much, Speaker. Most welcome. بسم الله الرحمن الرحيم والصلاة والسلام على سيد المرسلين سيدنا محمد وعلى آله وصحبه وسلم. I'm going to talk about photovoltaic. It's one of the dominant technology in renewable energy. So we will go through this technology and what is the benefit of this one and the advancement. Actually, the photovoltaic, it depends upon solar energy. Solar energy is one of the free energies we are getting, but we are not utilizing it in a proper manner. So the new scientific research is utilizing this technology for the last 30 years to be a proper technology to supply the clean energy. We have some facts actually for the solar energy potentials. Every day the earth receives too much energy from the sun, which it is consumed in all other resources, so it can cover all other resources if it's utilized in a proper way. We have actually estimated and roughly calculated for the Saudi Arabia that what is the need for the land to erect the photovoltaic, and we found out that the land of 4 by 4 mile parcel of the land will be sufficient for Saudi Arabia to cover its entire energy as all. Actually, the sunlight falling on a typical house can provide 1/3 to 1/2 of its heating energy. Today, solar energy, it's account for less than 0.05% actually in total renewable energy in Saudi Arabia. We can see here the solar power system installed in the areas defined by the dark discs. We can see that those discs, if they are utilized in a proper manner, it will supply the electricity for all the world. And Saudi Arabia is locating in one of these hotspots of the solar energy. How much utilized for the PV installation? We can see from the European Photovoltaic Industry Association that Germany is the country of #1 of utilizing the photovoltaic technology, one of the countries that utilize it in a proper manner. So they have 28%. Then China, Italy comes next, and Japan and the United States, and the remaining European countries, they have some certain low percentages. Here we can see the global regional PV installations. If you can see in the Middle East, how many watts per inhabitant we will see. Unfortunately, we are in the hotspot of solar energy, sunshine, but we have still not utilized it in a proper manner, while in the United States, they have utilized it in better way, and in Africa also, where the hotspots and where the high solar radiation occurring is also, it's very low. Because the technology is at the moment expensive and it needs a background to utilize it in a proper way. So the advantages of the solar energy, as we know, it's clean, it's sustainable, and it's free. So we don't need somebody, to supply us. It's supplied by the God through the sun. But the disadvantages, of course, its reliability depends upon the location. It's a part-time, so it's during the day, less efficient and costly equipment till the moment, but is going to be advanced more and more and to be much more efficient due to the high research going on. And if we look to the solar energy potential, so photovoltaic technology is accounting for 1% of all renewable energy technologies. So it's still mature to be utilized. The amount of solar energy reaches the Earth's surface every hour is greater than the mankind's total demand of energy in 1 year. So that photovoltaic system can utilize it can be one of these options to utilize such a huge energy, which it is free and coming from the sun. We know that the solar radiation coming from the sun, it has some reflecting radiations, direct one and diffused one. The photovoltaic cell, how it operates actually, it depends upon 2 layers. We call it p-n junction. positive layer and negative layer, so that when the sun rays fall in on the cell, it will, the photons will emit the free electrons. These free electrons will be freed from positive layer into negative layer, so that it will run the electricity. Sorry, just. So the PV array, it consists of a cell. This cell will be part of the module, and the module will be a part of the PV array for producing a huge amount of electricity. Actually, PV arrays, they can be connected in series and in parallel. And if they are connected in series, the current will be the same while the voltage will be added. And if they are connected in parallel, the current will be added and the voltage will be the same, as we can see from those two figures. So the most important things for the photovoltaic is how to locate this one. Otherwise, you will minimize its efficiency. So the panel angle is very important. It has been found out by many researchers that the panel angle will depend upon the altitude of each country. Also, how to follow the sun when you erect or when you install a PV panels over the roof of the house. It is very important to know how is the direction of the sun, especially in summer and winter. And at the same time, there will be some certain calculations. But as I said, all in all, you should install your panel on the roof of the house, that it depends upon the altitude of the country you are. So the PV system, it has many components. We have energy conversion, energy inversion, and then energy storage, which it is the battery. And from the energy inversion, it goes directly, if it needs DC, it goes directly to the DC supply, or it can be energy distribution. It can be sent out through the metering to the electric utility. So the solar array, it has a storage so that this intermittent supply of energy can be utilized in a proper way by using storage. The flexibility, actually, the PV, one of its advantages that it can be standalone. This means that it can be used in remote areas where it is very difficult to get an electrical utility supply, or it's an isolated regions. So the standalone can be used for house appliances, water pumps, fans, and etc. It has a battery backup, or it can have a generator backup. The generator backup, which it means a diesel engine, a wind turbine, or any other resources, so that the engine generator, like wind turbine or diesel engine or etc., gasoline engine, can go to the rectifier, to the battery, and can be supplied either a direct DC load or an AC load. The solar cells types, there are many types of solar cells. We have a first generation and we have fourth generation. Still, the advancement and research on PV cells is going on in many research centers to make it more flexible, to make it more reliable, to make it more efficient, to be utilized properly. So we have the first generation single crystalline silicon. The second generation is amorphous silicon, polycrystalline, cadmium telluride, which it is one of the dominant one. The third generation, it consists of the new technology which is called nano crystal solar cells. We have photo, electrochemical, gradual cells, polymer cells, and dye-sensitized solar cells. The fourth generation, which is coming up and which it has a good efficiency and reliability, it's called hybrid inorganic crystalline within a polymer matrix. So that these can be, some of them, they have advantages better than the others or more benefits than the others. We can see that the monocrystalline silicon module, it's more efficient commercially. It is used since long time, it has proved that it's a good technology, but not that efficient, so that they have produced polycrystalline silicon model, less expensive, but little bit less efficient, but it can be actually utilize the spaces, because one of the disadvantages of monocrystalline silicon that there are a huge gap of spaces that is wasted. So that one, it can be in a square shape, utilize all the area. Amorphous thin film, which is coming on, it's used for military and different human resources. It's a flexible. Metal grid is replaced with a transparent oxides. Its efficiency is a little bit lower, but its reliability and flexibility is making it more common to be used. So the advancement in BV technology, especially the fourth generation, one of its features is that it's a multi-junctions, so that it utilizes all types of the lights falling on the cell. So it increases its efficiency. So it depends upon polymer solar cell and multi-junction technology. Future advances actually relies on the nano crystals. So this nanotechnology, as we know, it's proved to be a much enhanced technology for many devices. So such as cadmium telluride tetrapods. You can see here with the advancements in the technology of manufacturing with the BV cells, we are narrowing the gap between the theoretical higher efficiencies as we want and the practical ones, or we can say the existing efficiencies we get from the real BVs. So here we can see that the efficiency is increasing a little bit with the new advanced technologies of multi-junctions. It has raised up the efficiency up to nearly 40%, which it is good for a proper utilization. Here, the current voltage curve, actually, it shows us what the maximum operating point where we will have high power coming from the cell. Through these characteristic curves, we can know that what is the effects of many parameters on the BV cells. We can see here that the BV cell temperature, if it increases above 25% for each degree, the module voltage will be decreased by 0.5%, which is not suitable for high temperature regions. Suppose such like Saudi Arabia, we have temperature in summer sometimes reaching 50 degrees. So that this one will make it deficient, the BV cells. But the new cooling systems going on, a lot of research, and we are involved in it, the cooling systems with the manufacturers and research centers, they are producing or supplying to the BV cell itself, it will narrow this gap and these disadvantages. But the other things also, the insulation. Low insulation, it will lower also the energy output from the BV cell. So that the other things we have, the good things we have, that we have high insulation, but we have high temperature, which it affects the BV cell electrical output.
2 minutes remain.
Yeah. So the BV time, actually, it's from 20 to 30 years. Efficiency decreases by 1%. BV efficiency at the moment, it has reached up to 25 to 30%. The prices is coming down, as we can see from the United States. The Department of Energy's Solar America Initiative that found that since 2030, the price of the BV cell will drop dramatically. We did some economical analysis for a small house in Saudi Arabia, and we said that if this house has an electrical bill of 165 riyal per month, if we multiply it by 12 months, it will be 2,000. If we multiply it by 10 years, it will be around 20,000, while the cost of the BV system, it will cost around 17,000 plus 25,000 of the operation and maintenance. so that it will be 45,000. So the payback period will be between 10 to 15 years. So it's not that beneficial. But if we do a mega project, it will be beneficial for all the houses. But for smaller house at the moment, due to the cheap electrical bills or the cheap electrical price, it's not that efficient. PV application, it has a lot of applications in solar cars, in resorts, isolated resorts. Here we can see the PV array of 3 megawatt in Sacramento, and also in Chicago they have another station of 10 megawatt. I have seen also a station in Germany with 50 megawatt. It can be used for remote areas in aerospace technologies, in the offshore, and etc. So there are many applications in Saudi Arabia. In Saudi Arabia, they have established a lot of research centers. They were trying to do a pilot projects for the PV cells. We can see here Solar Village, Solaris, 350 kilowatt. It has been actually applied long time ago to produce 1.5 megawatt hour. They have also solar hydrogen demonstration plant. It used to be one of the world's first plant for producing the hydrogen from solar energy. It has been used in also for a tunnel, transportation tunnel light. There are a lot of research going on at the moment at KAIST to actually see whether the PV, how it can be utilized in proper manner in Saudi Arabia. They have calculated the cost of kilowatt hour of 10 cents per kilowatt. So we can conclude actually from this great benefit from the PVs that the PV system can convert the free energy into an electrical usage energy. It's clean, so it's not polluting the environment, and it's one of the major renewable resources. It has proved its value. Here in Saudi Arabia, it's not that economical to use it for the residential, but for the mega project can meet the current and projected Saudi Arabia energy. So the huge mega project here in Saudi Arabia will be one of the good options to reduce the pollutants from the conventional power plants. Thank you very much for your listening.
Thank you. Thank you, Professor Omar. Excellent presentation. Second sessions, it is related to the future of innovative integrated solar combined cycle. This is a presentation. It is about the technology of Kraft and Lagen, Munich. The presentation, it will be presented by engineer Garrett Cole, is the head of business unit Energia, power plant technology division at Kraft and Lagen Munich. Please.
Yeah, good morning, Mr. Chairman. Good morning, gentlemen. Thank you very much for SEC to give us the opportunity to present here our technology. And I would like to talk today about the future concept of an innovative integrated solar combined cycle. Okay, now it works. I would like to start first to introduce my company. I think the most of you will not know us. We are in Germany since 90 years, an important role in the area of energy business, but we have not yet been intensively here in Saudi Arabia. So maybe it's interesting to spend some words first about who we are. We are one of the leading companies in Germany for piping, power plant construction, and we cover 8 business areas where we work for all kind of installations. We are active in the energy and environment business as an EPC for combined cycle for all kind of power plants, and in this business area we also cover the solar technology. But on top of that, we also work in the decentralized power stations like gas engines, smaller gas turbines, heating systems, and district heating systems. This is under the underground piping systems. We also work as piping contractor in the nuclear business. We have been working there since the beginning of the nuclear industry, and we are still there, one of the few companies that are certified in Germany to work in the piping systems for nuclear plants. We are working in industrial and petrochemical plants as an installation company. We also work for HVAC firefighting systems. We have a business unit that works in the engineering and consulting, and we have pre-manufacturing for piping systems. We can bend high-pressure pipes, diameter 1100, wall thickness 140 millimeter, and we can inductively bend these systems. But enough with that. I would like to talk today about the solar energy, and thanks to my colleague that has talked before, there was a short introduction to what is solar, and I would like to talk not about the PV, but about the solar thermal power plants that are covered under the aspect CSP plants. That means concentrating solar power plants. And there are different systems, and just to give a short resume, the next person that will be talking about another systems. To give you an overview, there is the Fresnel technology, flat mirrors, then the parabolic trough, bended mirrors with a receiver pipe in the middle. There is the tower technology and the Fresnel technology. We have took the option for tower technology because that offers a high concentration factor. That means high temperatures at the receiver, high temperatures at the heat transfer medium, and that means high efficiency. We want high efficiency for our plant, but, and this is what I will be talking about in a minute, it's important also to offer dispatchability. We have heard yesterday that even here in Saudi Arabia, and we are experiencing that in Germany since a couple of years now due to this high content of renewable energies, we need to have dispatchable renewable energy that offers the possibility to deliver the renewable energy whenever it's needed in the grid. And the grid makes certain changes, and we want to follow it. So we have developed since the last 15 years, together with the German Space Center, technology which is called the open volumetric receiver. What you see here in this overhead is the receiver, how it works. So that's a ceramic structure. We take ambient air, the fresh air from the ambient, and we heat it up in the receiver where the concentrated solar power goes to. So you see on the top of the tower there is a lighted point. All the heliostats, the mirrors, concentrate the radiation on this point, and there we find this ceramic structure. We take air into the receiver. The air heats up to 600-700 degrees. And the important point about this technology is it's air, ambient air, no oil, no molten salt. So it's a very simple and cheap medium. And the second point, and you can see it here on this overhead, is the receiver heats up. It heats up to 800-900 degrees. And we all know the losses of such a receiver is the radiation that the receiver from his heat gives away. So as you see on this overhead, the temperature, the highest temperature is inside the receiver. So we have kind of a protection of the receiver against the radiation losses. So this is a schematic drawing how our technology works. You see on the bottom, you see the mirrors. They concentrate the radiation on top of the tower. We have a concentration factor of 1,000. So we have 1,000 suns on the top of the receiver. Per square meter of heliostat field, of mirror field, per 1,000 square meter, we have 1 square meter of receiver surface. That means we have up to 1 megawatt concentration on 1 square meter of the solar radiation. Then we take the air from the ambient, as you see, and it heats up to this close to 700 degrees, and we can go to a normal conventional boiler. After a normal conventional firing, we have this hot gas, hot air with this 700 degrees, and we take it to a conventional boiler and to a steam turbine, and the rest is a conventional power plant as you know it. But on top of that, in the middle you can see the storage, and it's again a big a vessel with a ceramic structure inside. The hot air goes through it and it heats the ceramic up, and when you go then from the cold side on the bottom back through the storage, you can heat the air up and you can bring it into the boiler. So that means you can heat up the steam again and produce electricity on the turbine. This is shown now here in this overhead, and you can see we can go in parallel during the daytime operation to the storage and the boiler. So during the day we fill the storage, and that means that for the later afternoon or evening you can produce electricity from the storage. The cold air is then recycled and is going back to the receiver and is sucked back in again. What happens now in the morning or when a cloud goes through? You see there is less energy from the receiver, but we can compensate it now from the storage. That is one function, so you can keep the electricity output constant because you compensate a part of the energy that is missing from the heliostat field now from the storage. But you can even during the night, you can see now the receiver is not working anymore, but we can circulate the air inside now between the storage and the boiler, and that means that you can even produce electricity during the night when the sun is not there. But you can also do, and that is something that we have investigated, you can follow load profiles, and I will show that in a minute how it works. But first, a little bit about how does our technology work. We have developed an own heliostat. Heliostat is this big mirror that follows the sun. And we have, in this design, we have made a big focus on keeping it simple. Because we know it will be installed in areas of the world where there is tough ambient conditions, difficult ambient conditions, and also normally not very high labor force. So what is needed there is a very simple construction that can be easily replaced, that can be easily also produced in other countries. And we have a patented design for this heliostats, and that is special focus on simplicity. The next important component is the receiver. I talked about it. You see it consists, this is a photo against this receiver, this lightning point on the top. You see it's a black surface. So the radiation is captured there, and it works, as I explained before, like a trap, a radiation trap. So it heats up, and it's a ceramic material, so it can be heated up very high, and it's very resistant against a difference in temperatures. So that means your heliostats, your mirrors, doesn't have to be so precise, so exact. And again, that means less cost and less demanding workforce you need to produce them. And the receiver is, and that's very important if you compare it with molten salt or oil receivers, there is nothing inside. So it means you can easily heat it up in a couple of minutes. The plant is fully working. And if the sun goes away or you want to stop it, in a couple of minutes, it's cold also. So that gives a very, very high flexibility. And it's very resistant against problems of operation. So let's come to the next important component. It's the heat storage. As I explained, it's also a ceramic structure. And as you see, we flow the hot air over it, and then it heats up. And with the cold air from below, then we can take the energy out again. But what is important about the storage is that it's no moving parts inside, no fluids inside that can freeze in, that can leak out. It's a very simple construction, again, very resistant. We are operating it in our testing facility in Germany since 7 years without any major problems there. And the last point, which is also very important, when we talk about cost of production, the important point to make solar energy flexible is the cost of the storage. And we have the cheapest storage in sense of price per stored energy in this storage. So let's quickly resume this technology. What does it mean? We have a very high reliability and operational safety of this technology, a high availability due to this part load behavior. We have a low operational cost because we have no moving parts, no flutes, nothing that can pour out, and also that means it's very ambient friendly. A very high system efficiency because we operate at 800 degrees. All engineers below among us, we know that the Carnot efficiency depends on the highest process temperature. So that is why we have no limitations like in the oil systems where you're limited to 400, 500 degrees. We can produce, and I think that's the most important, energy on demand whenever it's needed, and we can easily hybridize. And we have made a small case study, especially here for Saudi Arabia. How can we integrate that into the system here in Saudi Arabia? And one last important advantage is, of course, it can be highly there can be a high local content in the manufacturing and production of the system. So looking to this case study, you see the same picture again as I just showed, but it has been added a gas turbine. So what we can do is, beside an existing gas turbine, we can put the same system, and if you divide the picture in several components, you see here the gas turbine, and you see here the conventional power plant, and together they are a combined cycle plant, and you add the solar plant to it. So you have a full flexible project that covers all possibilities of flexibility. And our case study was now on an existing site with an, for example, LM2500, 20 megawatt electrical output as a demonstration. What would be the output of such a solar combined system? And you can see that our calculations resulted that we can put 20 megawatt from the gas turbine and 20 from the steam turbine, roughly. I show some more exact figures in a minute. So at a site, we assume Tabuk, where, due to the very high radiation of 2,800 dNi there, and the existing open cycle, we can produce 40 megawatt, and incorporating this 374 megawatt thermal storage, megawatt hour thermal storage, we have this full variety, and that's, I think, the big difference with all the other combined systems. We have a solar share of up to 50% in this system, but maintaining the full flexibility, especially if you talk about remote areas. These are the load curves that we have produced in these special case studies. And what you can see is we can, in the first picture, we can produce a normal flat load profile with a steam gas turbine and the fossil together with the solar. But you can switch in the second picture the conventional plant off, and you can fully provide the electricity by the solar system. Or, and that is the picture on the right side, we have taken the daily profile of the electricity grid consumption here in Saudi Arabia, and you can see we can, with this system, exactly follow the grid profile. The demand on the grid can be fully covered by this solar system due to the storage. This is a short resume of all the technical data. I assume that this presentation will be made available to you, so you can look at it and you can resume this data. You see 40 megawatt output, 21 from the gas turbine and 19 from the steam turbine. We have a receiver thermal output of 90 megawatt. We have 130,000 square meters of mirrors and a heat storage capacity of close to 400 megawatt hours. So the annual yield is close to 300 gigawatt hours per year, and that is more or less the general figures about this plant. So last words, what is our intention for Saudi Arabia? We are together here with partners, and we would like to give the partners the chance to produce time by time as much as possible here in the country, because we believe it's too big effort, too expensive to bring all the components from outside. We have a design that allows that, so we want to license this technology and work for the country, for the Kingdom of Saudi Arabia as quick as possible with a license partner and go together, transferring as much as of the know-how as possible, as quick as possible, and deliver maybe some key components, but try to develop this here as far as somehow possible. So, last overhead, quick summary.
1 minute, please.
Yeah, I'm fully aware of that. The usage of a non-pressurized air receiver with this simple heat transfer medium offers us the possibility to very simply integrate solar with the existing gas turbines here. We are proposing a small system as a demonstrator for the country to learn here together how to do it, and the plant can deliver energy on demand. As it was discussed during this meeting, during many presentations, that there is a need to follow the load curve. We feel that in Germany very strong. You will start to feel that more and more. The more renewable systems that you cannot control so easily are in your system, and we have the solution for that. Thank you very much, gentlemen, for your attention.
Thank you, Mr. Gret. It is very excellent presentation. Second presentation, it is related to the Duba project. Mr. Ignacio from Enetic Energia company, he will present it. Thermo-solar Energia, integrated solar combined cycle power plant, Duba Green project. Mr. Ignacio is the Director of Engineering and Procurement of Enetic Energia. Please, Mr. Ignacio.
Hello, good morning. First of all, I would like to thank you, SEC, to give this opportunity to participate in this important forum and to do this small presentation. First of all, I would like to do a brief word about our company, Enetic Energia. That is an EPC contractor in the energy sector. We belong 100% to one of the biggest construction group of the world, ACS, and we have experience over 50 years in the energy sector, doing engineering and construction of power plants in all kind of technology, fuel, coal, combined cycles, and of course in thermosolar. So the idea of this presentation is to explain a little bit the solar technology. Well, my colleagues has made a great presentation about that, and I will be focused on CSP technology, and especially in parabolic trough. I was the project director of 2 thermosolar plants in Spain, and now I'm the project director of Duba Green project. Photovoltaics, as you know, there is the different technologies. We have the photovoltaics that the professor explained perfectly, so direct production of electricity. We have also between the thermosolar technology, we have Fresnel technology, where a flat mirrors focus to a tube produce direct steam. And then we are focusing in CSP, in concentrated solar power plant, where we have different DC Stirlings with the motor Stirlings, and the other 2 most well-proven technology that are the solar powered tower power plants and parabolic tower plant. As Gerrit explained it, the solar tower plants are focusing in as heliostat field, focus radiations to a solar receiver that is placed in a tower of 200 meters height. And he explained one technology. There are other ones in the market that is using direct production of steam, or with a mixture of molten salt with nitrate sodium and nitrate potassium that makes more dispatchable the plant. The issue is that you heat the hot fluid, and with that, through a solar steam generator, you produce the steam that is used in a conventional steam water cycle. And then you can use, like another steam water cycle, you can condensate through a normal surface condenser, or through air cooler condenser, or depending on the availability in each of the site. The other technology that probably is the most installed, at least for example in Spain, we have more than 50 plants that are in operation, is the parabolic trough power plants. In this case, what we have is a solar field that is composed by parabolic trough elements that what make is use the radiation to focus into absorber tubes, where heat transfer fluid, that is a mixture of synthetic oil, heat the oil until 400 degrees. This heat transfer fluid is used as the same concept in the tower power plants. Is used in a solar steam generator in order to produce steam, and then is used in a conventional steam water cycle. In many cases, there are two possibilities: is with a thermal storage system. In such case, part of this solar field is oversized and is used that during the day when there is good radiation, is used. Part of this radiation is used to heat the oil in order to direct production of steam and use it directed to the turbine. Another part of this radiation is used. This duty is used to heat molten salt that has a very big energy and is stored in a very big tanks. And when there is no radiation, or during the night time, is used to discharge this molten salts, producing and heating the HTF. What we get with that is that at the end, the operation hours of these power plants increase dramatically, and at the end you got a higher production. With good dispatching of the plant, you can get more than 20 hours per day of operation in this plant. And then the hot starts and the cold starts of the plant are reduced, and you get a better efficiency. At the end, this parabolic trough is the principle is very simple. Is you have a parabolic trough in the solar field, where the idea is designed to collect all the heat radiation and direct it to a focus point that is part of a parabolic form. The main components of this parabolic trough we are going to start to see is we have some pylons where is supported all this parabolic trough. And some of them has a mechanism that allows to do the sun tracking and focus the sun and get it to direct the radiation to the absorber tube. This is called the drive pylons. These drive pylons, what this make is supports the structure that allows to support the great torque that appears in the structure due to the movement tracking the sun. There are two technology or two forms to this design of torque structure. Is torque tube, that is the one that is included in this slide, and torque box. This is exactly the same concept, but instead of making a tube, is making by a frame structure. What is the difference? Well, the torque tubes is probably cheaper for manufacturing, but the logistics gets more complicated because it has to be galvanized, and then for the transportation you transport a lot of air. It's good issue if you have the manufacturing installation very close to the site. Also, you have less construction at time. The time construction for this configuration is less. And in the torque tube, the big advantage is that it's a little bit more expensive, but it's a little bit more cheaper in the manufacturing, but it takes more time the erection. Once that we have the pylons and the torque tube, we have the cantilever arms that are used to support the mirrors, the reflector panels. Then you have installed the mirrors that are ball jointed to the cantilever arms. These mirrors are panels that has a high reflectivity and are used to make the parabolic form to the trough that allows to direct all the radiation into the absorber tube. Once that we have the pylons, we have the torque tube, we have the cantilever and the mirrors, we have the HCE supports that his purposes are to support the HCE absorbers that goes in the middle, in the focus of the parabolic form. These absorber tubes are vacuum tubes, are glass, and within the tubes is the heat transfer fluid. This has a good absorption, and we are talking about close to 96% of absorbability. And this is what is called a solar colored element. This is the unit element of the solar field. And a standard solar field, one that you have one solar colored element, and a standard solar installation is that with 12 SCE you conform as SCA, and with 4 SCA you conform a loop. That is the unit of the common unit of the solar field. Depending of the radiation that you have, depending of the amount of steam that you want to produce or the duty that you can produce, you calculate the number of loops that you require and of course the surface of mirrors that you require for your production. Then it's clear is the heat transfer fluid in cold is directed through the solar field, and then after coming back from the loop, you get the heat transfer fluid hot. All the loops are tracking the sun from the east to the west, depending of the time of the day. They have in each drive pylon has its control element that is called LOC, and this is due to a formula that is tracking the sun and another sensor that knows perfectly where is the position of the sun in every moment. They make correction and do this tracking of the sun. The concept is this transfer fluid has special properties, and there is works properly from 12 degrees more or less until 400 degrees. If you get over these 400 degrees, the properties of this heat transfer fluid get degraded. So sometimes during the summer and during the big radiation days, you have to do some damping and miss the focus of the trough through the sun in order not to continue heating and not to pass these 393 degrees. The idea is that in each loop, the temperature for the inlet of the heat transfer fluid is 293 and the outlet is 393. So the delta increase in its loop is about 100 degrees. During the same way that I said, if you overpass 400 degrees, there is problems in the heat transfer fluid. There is also big problems if you get cold this heat transfer fluid, because below 12 degrees it gets solid. So, and if it gets solid, believe me, it's a big problem in the plant, because you have to heat the pipings and can create very big problems in valves and instruments and so on. So
this oil that during the day is pumped around 40 bars, or depending on the sizing of the solar field, through the HTF pumps, during the night has to be continuing circulating, and it depends on the number of days that the plant is not in operation due to the bad weather or so on, has to be used HTF heaters to continue to guarantee that temperature doesn't get below these 12 degrees. Of course, there are other auxiliary equipments to allow these expansions and of the oil, because at the end you have oil with a low temperature. That you increase the temperature, there is an expansion that has to be assumed by the system. So there are some expansion vessels that allows to manage these expansions of the fluid. This heat transfer oil, when it's heated, is directed to the solar steam generator, where you put the hot HTF and water from one side, and then you produce the steam. Here you have a brief resume of more or less what, according to our experience, which are the operation hours of this kind of plants. Without thermal storage system, we are talking about 2,800 hours per year, and if you can use thermal storage system, we are in the best way you can get 4,000 hours. This has a very big advantage, the thermal storage system, because, as I said, you increase the production of the plant, because at this moment, the cost of the installation is continuing being quite high. We are talking about 3.7 to 4 euros per watt, and depending on the number of hours the production that you are getting you are able to get it, it makes you more, the business model of the plant gets much better. In Spain, due to very special condition of the subsidies related to this plant, all the plants for 50 megawatts, including thermal storage, were built in 24 months. That was really a challenging issue for get these projects in operation. This technology is the one that has been applied for Duba Green project, that, as you know, was awarded to a consortium to Initec Energia and SSCM, and that is around now in execution. Is exactly the same concept for the solar field. The only issue is that instead of the steam generated in the solar steam generator, instead of be directed to the steam turbine, is integrated in the heat recovery steam generator of a combined cycle. So this gives a very big flexibility in order to increase the capacity and, of course, the efficiency of the total combined cycle. We have here a small, I hope it works. We had here a small video of the 3D model of the power plant, and you can see the sizing compared with the solar field related with the combined cycle, the sizing of the solar field and how it's integrated in all the project. Okay, this is Duba layout, and this is the modeling that we are preparing with. We have these tanks. This first tank is the water tanks. We have as you know, there are three fuels in this project: natural gas, condensate gas fuel, and Arabian Superlight. We have a very big substation in 380 kV and 132. We have this is a facility for buildings, and then we have the solar field, as I explained it. This is the main heaters for the HTF, and the different loops for heating the oil that is directed to the solar steam generator. You can see there the steam and the gas turbine buildings, and of course the heat recovery steam generator. And in the other side of the rack, you can see the solar steam generator that is integrated in the pipes for the combined cycle. So you can if you can compare and you can see which is the size of the combined cycle of a standard combined cycle, and if you compare with the size of the land that is required for the solar field, it's amazing. Like a quick resume of the Dubai Green project. As you know, there are it's 2-on-1 configuration with two gas turbines, one G7FA04 and 7FA05, and a steam turbine also of GE, and HRG generator from Doosan that are supplied by SEC. And we do the rest of the integration of the project and of the combined cycle. This solar field is, we are talking about of 100 megajoules per second with a direct normal irradiance of 800 watts per square meters. And with that, we guarantee that at the reference site condition, we have this solar field duty integrated in the combined cycle, and we have 950 operating hours for 100% of the solar capacity, based in the typical meteorological GR of P50. The conditions where the steam are produced is steam superheated in 130 bars and 380 degrees, and integrated at the HP superheated inlet.
1 minute, please.
Yes, I'm finishing. Let's finish. In this quickest scheme, you can see how is integrated the solar plant in the PFD of the total project. How at the inlet of the HP superheated, we introduce the HP steam, and during the startups, this steam is directly to the condenser during a bypass. And once that we got the conditions of the steam to be integrated in the HRSG, this steam will be directed then to the HRSG. And of course, it's exactly the same for the feed water plant, feed water that comes from the combined cycle to the solar plant. Thank you very much.
Thank you. Thank you, Mr. Ignaiso. It is very excellent presentation. The four sessions, it is technical challenge of renewable energy integration in the Saudi Arabia. It is presented by Dr. Thamir Al-Buthami. Is an assistant professor, School of Electrical and Computer Engineering Department, King Abdulaziz University, PhD in EE from Georgia Institute of Technology, research in the area of smart and intelligent electrical system, modeling and simulation of complex system. Dr. Thamir, you can start.
Okay, thank you so much, Chairman, audience. Assalamu alaikum wa rahmatullahi wa barakatuh. In this presentation, I would like to talk about the renewable generation resources integration challenges in Saudi Arabia. Basically, this is the agenda of the talk. First of all, I will, instead of talking in a smaller scale as my previous colleagues, I would like to talk from a system level. So I will be zooming out and talk about the power system impact if we have a large integration of renewable resources. So if we divide the power system in two areas, for example, power system planning, power system operation, quality, we have a lot of challenges that the researchers and academic and industry need to be addressed when we want to have large integration of those renewables. For example, power system planning. As we all know, traditionally transmission planning are being driven by the load center. So when we have a really large load somewhere in the city, so we will be planning for constructing a transmission line to there. However, then due to the renewable generation, we need to rethink that. Nowadays, the driver has been changed to the renewable generation plant, not the load center. And also the wind and solar power forecasting technique must be recalculated again, because of all these resources, solar and wind, they are intermittent resources. So we don't really know when the cloud will come and cover our solar plant, and we don't really know when the wind will blow out. So advanced techniques such as neural network, stochastic analysis of the solar irradiance, as well as the wind speed. We need to have a lot of tools to basically and accurately forecast these resources. For the power system operation, basically there are two operational functions that are most affected by the alternative energy integration, and those are the economic dispatch and the unit commitment. And basically those, due to the intermittent nature of these resources, those resources are considered to be not dispatchable. Current technologies, yes, we are seeing nowadays that the wind plants or wind farms start to be dispatchable, and also advanced control system have been also implemented in the solar PV to basically allow it to be dispatchable. For the system stability, the expected of integrating a large number of renewable resources will have an impact on the system by reducing the system inertia. Conventional units, they have a rotating mass so that they have basically inertia in those rotating mass. However, on the other hand, for the renewable energy resources, we don't have rotating mass, especially in the solar. So we have less inertia in the system as we basically increase the percentage of integrating those resources. On the power quality also, we have the impact of the power converters. We basically, the technology, the solar PV, as well as the wind turbine, they are basically connected with the grid or coupled with the grid through power converters. And those power converters, they work through basically IGBTs or thyristors. So due to the IGBTs, the switching devices, they are the waveforms that are being generated basically when those waveforms go through converting. They have been rectified and then inverted into AC. So due to these basically changes, there is harmonics in the system, and also flicker due to the voltage fluctuation. In this basically presentation, I would like to go deep a little bit in the stability area and show you a little bit what would be the impact of integrating a little bit up to 20% penetration of solar PV on a power system. Okay, before we show the impact, let's have a look at the time scale of the power system operation and control. So we have basically the conventional power plant, and we have the solar PV, we have the wind. So if you look down, there is the time scale, which goes from 4 days, okay, up to 1 millisecond. So in this, we would like to disperse the power system control events, as well as the solar PV and wind turbine. So if we basically projected this conventional unit, we have all the controls, the excitation, the governor, the power system stabilizer, or disperse above this time scale. For the solar, for the wind, I'm sorry, for the wind, we have also projected a large plant or a large farm of wind, sized 3 different sizes, basically 25 megawatt, 50 megawatt, and 100 megawatt. And each one is basically shown here. So for example, the pitch control of the wind, the blade itself, it takes about 10 seconds to 10 minutes basically to perform the control and avoid any instability in the system. For the solar, however, the medium to fast cloud will have an impact in this time frame for different plant size, 25, 50, and 100 megawatt. There is a common factor between the solar and wind, which is the converters. And the converters basically is the mean where we could couple the solar PV as well as wind type 4, which we'll talk about with the power grid. Here is basically the area of the focus of the presentation. We would like to focus on the area between 10 to 10 seconds or to 1 minute. And we would like to see exactly, zoom in this area and see the impact of having a large penetration of solar and the stability of the system. So the system stability basically is kind of an obscure concept to some people. So this is why I put this slide a little bit. So if you look here, basically the question becomes, does the system return to an acceptable condition within the first minute of being perturbed by a generation loss or a transmission line outage? So basically, if you look here, the blue round circle represent the conventional generation plants. And the green wrapper basically represents what we call in academia the infinite bus. And the connection between all these poles and the infinite bus are rubber. And the thickness of the rubber basically represents the capacity of this generation. And the hands basically represent what? Represent the solar PV plant or a wind. So if you look here, we don't have any inertia. So these basically, if we have a scissor, which represents a line outage or a generation, if we cut one of these line or a generation, then the system will basically wobble until we get to a new stable condition. So if the wobbling basically is too severe, if we lose the largest power plant in the network, then we might have an outage or a blackout. So that the load basically will, instead of having one rubber has been cut, we'll have a cascade effect. We'll have another rubber and another. This basically, in a nutshell, the stability problem. Okay, for the solar, there are in the literature there are several models of the solar PV, solar and wind. For basically the solar, there are two different types. The concentrated solar thermal, or the CSP, the concentrated solar power plant, or the photovoltaic. For the CSP, which is shown in the left here, this is basically has been my colleagues have already detailed upon this technology, and they talk about the different type of these technologies and how do they work. So no need to go back to this. For the PV solar, for the photovoltaic, on the other hand, the PV basically is represented here by two different models. Those are basically the electric circuit of the solar, for the solar cell. So if we now represent the PV cell in a simulation software, we basically use one of these electric circuit. So this is basically for the solar. What about the wind? We have four different type of wind turbine. The first one is the fixed speed squirrel cage induction generator, and this type kind of like a little bit obsolete right now. This is a small scale wind turbine. It goes in the kilowatt, and basically as the name implies, it consists of a squirrel cage induction generator driven by a fixed speed wind turbine. The advantage of this one is the low cost. However, it has a disadvantage, which is it draws a lot of reactive power from the grid. This is why we connect a capacitor bank where it's connected to the grid. The second type, which is the fixed speed wound rotor induction generator, and in this, as the name implies, basically it's the same one as the one before, but here we basically control the rotor. So we inject a rotor current, so we have more flexibility. The third one, the variable speed doubly fed induction machine. And this is the latest technology in the wind turbine, and this goes. It has a high efficiency, and it goes up to 2 megawatt and above. The last one is the variable speed direct drive, and this technology basically we connect the wind turbine with the grid through a full-size converter. So all the power goes through the converter, inverted into basically a DC controlled, so the active and reactive power are being controlled, and then inverted back into AC and injected to the grid. So to basically study the impact of a solar PV on the system, what we have already done is basically we use the power system simulation software, PSSE, and what we did is basically we exploited one of the library there is the wind turbine module type 4, which is the full-size inverter. So we said, okay, if we use that inverter and basically we program that to inject what is the output of the solar PV, then we have a model or a customized model of the solar PV, and we can do a lot of stability analysis study. So here, basically, we built the user-defined model, and in that model, we basically use the circuit that I showed you before, as well as the maximum power point tracking algorithm to basically extract the maximum power from the PV. And then the output power from the PV basically is being injected into the full-size converter, and from there we basically inject that into the grid. If you're familiar with PSSE, you would be familiar with this figure too. In this, basically, it shows that this is the PSSE network simulation, the simulation network, and that is the wind model type 4. And basically, you can see here that the equations of the solar PV are here, and then the output is the power that is being calculated from the PV and being injected to the electrical controller of the power converter, and then from there we schedule the power converter whether the active or reactive power. Okay, after we developed this one, we basically tested this on the 39 bus system for 3 different level of penetration: 5%, 10%, and 20%. As you see here, there are 3 plants. One is in bus 2, bus 31, and bus 29. So the input of the data, we would like to see an extreme case. Not an extreme case, but an actual case. So basically, we have an actual data of a solar PV plant, and you can see here there is a large fluctuation on a short time scale, a short time of period, and we would like to project this into the system, and we want to see how the system will react. So basically, you have a large fluctuation from 1,000 solar irradiance up to 250 watt per square meter, and this is a large fluctuation. When we basically pass this data into the simulation software, we have this response So if we have a sudden change of the solar irradiance at bus 38, basically we have this. We recorded this response. As you here see, the critical rate has been drawn in a dash line. Whatever below the dash line is not acceptable, and this has been set by the under frequency load shedding relay. So basically, we said, okay, if the critical rate, if there is a big change that is less than 6 seconds, that's not acceptable. This rate of change is not acceptable, and we need to do something about it. But if the rate is greater than that, this means that it's safe. So with a different drop in time, we recorded different responses, and we see that the 6 seconds is kind of the critical rate. And during this one too, in this case, we recorded the frequency of the system, and you can see that the 6 seconds rate, we have a safe frequency. The system returns back to stability. But if we have a rate that's faster than 6 seconds, then the system goes to instability mode. Another case, we apply a fault, a 3-phase fault at bus 39 with a 20% penetration, and this is what we have seen. However, this is just for 20% penetration. What about if we have large penetration? We've seen on the left side, this is the frequency response of the system. However, on the right side, this is the power response of the system. So you can see that basically the frequency fluctuates and then damped out. However, the low frequency oscillation took a little bit time before it fully damped out because of the penetration of the solar and the less inertia in the system. And on the right hand, you can see the conventional unit response as well as the PV plant for the power, the output power. Okay. There are other cases, and if you are interested, you can go back to the reference. I want to switch gear into the power, another topic that's coupled with the, 1 minute? Okay, then we'll skip this. But if you are interested, what we have done is we want to test this into the Western operating area. So what we have done is basically we don't have the system. So we basically built an open dynamic model of the system, and we basically test this, and we published several papers on this. And basically, if you are interested, you can look at the references. These are the response, and basically, given that there are a lot of there are a lot of challenges with the large penetration of renewables. This means that we don't stop of basically adopting these technologies. There are a lot of due to the advancement in technologies, controls, and forecasting. We have seen already that the wind has been already now dispatchable, and the solar systems, the solar PV plants, they have already now seen some papers that they can basically provide ancillary services to the grid, and we would like to also exploit this and study the advancement technology or these new technologies on the power system in Saudi Arabia. With that, I return the mic to the chairman, and thank you so much for attention.
Thank you, Dr. Thamer. Thank you, Dr. Thamer. I think your presentation is required more than 20 minutes. It's very short, 20 minutes, but after that, I would like to go to in brief for all presentation. First presentation from Professor Omar Badran. It is related to the PV. He's presented the advantage, disadvantage of solar energy and PV price component series connection and parallel connection panel gun. This is the angles, how to locate the panel, and the price and PV. Mr. Garrett, he's presented the CSP technology from Kraft and Langen, Munich, and he explained, also presented the case study and what's the advantage and what's the future for their technology. The third presentation, it is from the Enetic Energy, from the Mr. Ignacio. He's the project director for Duba. This is the project, it is award to the Enetic and SCCM. And he's explained the parabolic troche, which will be implemented in Duba, and the advantage and disadvantage of this technology and the heat transfer. The last sessions, it is from Dr. Thamer Al-Guthami. It is the challenge for implementation of the renewable energy, and he explained the model of wind and solars. And he, in the western region, some research in the western region. We can start now the question, please. Yeah, Abu Rayyan, please. Very brief question, huh? That's very...
For Mr. Garrett, thank you for your presentation. And just I want to make a comment that because in Saudi Arabia, our environment, the whole year is dusty and too much dust. And that can prevent the ray to reach to the concentrator because you are, fixing all the photovoltaic cells to send their rays to the concentrator. So that can prevent really in so many times rays to go there, so it reduces the efficiency of that method. In the meanwhile, regarding the storage, you didn't talk about the lifetime of the storage and the content. So, and also because like Mr. Ignacio talks about this, he also talks about storage, but he didn't brief or detail what that type of molten salts, the lifetime, and if that also methods can be implemented in your storage. But we don't know the prices, the molten salts, how tested, the regular time for replacing it, as like similar to the silica gel in transformer, it changes its colors and sometimes need to replace that. That's the question. Thank you.
Question about the storage.
So, thank you for the question. The question I would like to first address is the dust you have here. Very good question. And in the testing plant we have in Germany, we are in the area where we have this open coal mining, and it also represents a lot of dust. And of course, any solar system, PV, concentrating by trough or by tower, is always affected by this dust laid down on the mirrors. So the mirrors have to be cleaned. They have to be cleaned once in a while. Due to our experience, and maybe my colleague can also add something to that, for several times per year. But what we have found out is that is also a certain very simple labor that can be offered to the persons that are close to the area. And it's at the end of the day, if you look to big buildings, they have a lot of glass surface that is cleaned also continuously, and the cost is relatively low. Concerning the storage lifetime, also a very good question. We have experienced now, as I said, in the testing facility in Germany, 7, almost 8 years of thermal cycling, and as you know, it is a fixed ceramic structure, so no moving parts inside. It's very long-term resistant. That is to our experience. I hope that answered your questions.
I don't know. Yes. This, related to the question if the molten salt is well proven, I think more 60% of the 50 plants that are installed in Spain, more or less, are considering this installation of molten thermal storage system with molten salts. So it's quite well proven. It's also installed in another thermosolar plant in United States with a solar tower, a big one of 120 megawatts, and it's well proven. You have to take into account that these plants are young plants, because all of them are no more than 6-7 years. So there is a theoretical life of the molten salt, but it's not well proven. It's not to know if it's going to last the 25 years that is designed the plant. In the oil, we know perfectly that there is a system. There is a system to replace the oil because there is some degradation, and through the expansion vessel and the overflow, you can put additional oil during the operation. In the molten salts, at the end, you have some leakage or some drainage, and has to be there is some miss the level, and then you have to melt additional salts, and you have to increase the amount. So there is like you make some drainage and you incorporate additional molten salt.
I think Brian, he's very interesting for this subject, and after that you can communicate to Mr. Gnaisu and he will give you complete information. Yes, Abu Sultan, maybe he has. Yes.
Assalamu alaikum. I would like to thank the presenter for the informative presentation. Actually, my question to Professor Omar and Mr. Gret, with comparing the both technology for the CSP and the PV, if you consider the levelized cost of electricity, where do you think that the both technology will stand on the future market trend?
Shall I start? I think you have to see two aspects. Certainly, the levelized cost of a PV plant is lower than of a CSP plant. But our colleague has explained very well what happens to the system when you have a high content of PV plants without storage, where you can't control when they come in and when they go out. And then there is a cost you have to add, of course, to your system in order to control the situation. And that is the advantage of CSP, especially with the storage, as we too have explained it. You have a full flexibility, so you can, in the moment that, for example, PV goes out, you can compensate with CSP the outgoing PV and can levelize the electricity, and that means that you have a stable grid, and there is of course a cost related to it. But on the other hand, also with the size of the plants, of the CSP plants, there is a degradation of cost, and that there is a matching point at a certain level. That is what we believe.
Yeah, it's a good question actually concerning the differences between CSP and photovoltaic. The photovoltaic technology, it's a proven technology all over the world. We can see actually in Germany, they are getting around 30 gigawatt from photovoltaic. Even they have lower insulation, D&I, than in Saudi Arabia. I think so 40% lower than in Saudi Arabia. So that it's a proven technology. CSP is also one of the good technologies for high temperature regions like Saudi Arabia, because BVs for high temperatures, it will the efficiency will be degraded or will be down, as we have seen. But the CSP, it can actually withstand such high temperature. Both systems can be used in Saudi Arabia. Both systems, they are mature enough in technology. Because I was in Germany, I worked with the DLR, with parabolic troughs actually, and I have many publications on that, also on solar towers. BVs can be used in certain regions in Saudi Arabia where the temperature is low. Suppose like in the northern region, you can use the BVs. In the middle region, you can use CSP. Now, both technologies, they are suffering from obstacle, which it is the dust. Because the mirrors, you know, due to the dust and the BVs, the efficiency will be lowered down. So that, but there are now, they are tackling this obstacle by continuous cleaning. So these technologies, they are advancing due to the advancement of the, the tools they are using to keep the efficiencies as much maximum as possible. So all technologies, in my opinion, as I have worked with all of them, all they can be adapted in Saudi Arabia. It depends upon the region and the meteorological parameters in that region. So,
Thank you, Professor.
Yeah.
I think the time it is complete, but if we can allow for two questions, if allow 5 minutes from the break. It is allowed? Okay. 5 minutes from the break. It will be 5 minutes the break.
Assalamu alaikum. My name is Shafiqur Rahman. I am from King Fahd University of Petroleum. My question goes to Professor Umar and Mr. Garrett. Regarding the tracking system, as we are talking about the dust, we have a failure in solar village because of this dust. What you comment on the tracking system of the mirrors or taking the PV systems?
I couldn't catch actually the question, but
the tracking of
yeah,
the
yeah.
PV module.
Actually, the BV systems and the CSP systems, they are more efficient if you use tracking system. So most of these technologies, they are now used with the tracking system, of course, because the tracking system will increase the efficiency up to 30%, rather than using the fixing one.
So in the case of the CSP, especially with the tower, the tracking system is necessary because we have like a concentrating lens, as I have explained. We have a factor 1,000 suns on the receiver, so that means we have to track because the sun moves during the days in two axes. It elevates and it also moves in this direction. So what we need is a two-axis tracking following the sun, and it's a continuous process. You will not even really see it in very small increments. The tracking system has to follow the sun for each heliostat, and if you look from the tower down to the heliostat field, it looks like a big lens that moves during the day, its form according to the position of the sun.
Yeah, I would like to add actually one thing. Without using the tracking system, it's useless to use these technologies because the efficiency will be so low. So this is why all the manufacturers of these technologies, they have already adapted the two-axis sun tracking systems. It's well known since long time. Thank you very much.
Okay, thank you a lot for audience, and thank you a lot for thank you, Professor.
للمهندس عبد الرحيم الشيخ على إدارة هذه الجلسة. نكرم الآن رؤساء المتحدثين في هذه الجلسة. ايوه أيضا يكرم رئيس الجلسة المهندس خالد الطعيمي رئيس قطاع التوليد بالقطاع الشرقي. ننوه لسعادتكم بأن كل محتوى هذا الملتقى سيرسل لكم في رابط مشاركة لمن هم داخل الشركة وأيضا خارج الشركة. تبدأ الجلسة الأخيرة في تمام 11:10 شكرا لكم. والتي يرأسها المهندس أحمد العيسى مدير مشروع الأكاديمية الوطنية للطاقة.
Assalamu alaikum jami'an. Good morning, gentlemen. First of all, I would like to welcome you all and my speakers to the last session for today. It is related to the renewable and nuclear energy. We have 4 speakers. And before we start, I remind you again for the questions will be left in the end of the session. And also another reminder that still we can view your questions related to this session through the application that you have in your mobile. So looking into the 4 presentations, we'll start with the first one, which is related to the wind energy for remote village. And it will be highlighting the global demand for renewable energy, which is currently increasing, as well as the energy security in the future. The annual growth of power consumption in Saudi Arabia is estimated to be increasing with a rate of 7.5%. To meet this increasing demand, Saudi Arabia has already started using the renewable energy from the sun and the wind. The next presentation provide an overview of a project. Its objective was to study the techno-economic feasibility of setting up hybrid wind PV diesel system for a remote village called Radwat bin Habbas in Saudi Arabia. The presentation will be delivered by Dr. Shafiqar Rahman. He is the researcher engineer at the Engineering Research Institute at KFBM. He is PhD in mechanical engineering from University of Pretoria, South Africa. He has more than 20 years of research experience in surface and upper air meteorology, wind and solar energy assessment, wind, PV, diesel, hybrid power system design. Published and presented more than 170 research papers. Let's please join me and to welcome Dr. Shafiqar.
Assalamu alaikum wa rahmatullahi wa barakatuh. Thank you, Mr. Chairman, for your brief introduction. I would like first to thank the organizers, especially the SCC, for organizing such a knowledge-based meeting which brings the academia and the industry together. It was really very beneficial because today is the last session of the last day. And before I go into my presentation, I would like to just bring some points to the decision makers, because I have been working on renewable and especially the meteorology of Saudi Arabia for last 20 years. So what I want to give a message to be carried out so that it can bring some, thing into existing. Wind power is both technically and economically feasible. It has been proven worldwide. There's no doubt about it. The other thing, Saudi Arabia too has the potential, lot of potential on wind energy, because back around in 2000, early 2000, I identified 4 or 5 sites, windy sites that were based on PME data, and that was proven later on by CACS. They did some measurement at 40 meters. It was proven at that time, and now again, Saudi Aramco is using 92-meter tall towers like they did in eastern region and the north region, and it is proven that at 80 or 90-meter height, we have annual average wind speed of more than 7 meters per second, which goes to class 2 and 3. So it is doable. We should carry this message and try to convert it into reality, which as of today, we don't have, wind farms, in Saudi Arabia. And what it means, new industry and new jobs, okay? And jobs for administration, management, skilled and unskilled, in all levels of job. So just I wanted to give these points based on my experience, and I'll move to my presentation. Just it's an exercise you go through usually in academia, like why renewable energy, and what is the scenario, global scenario, and then I'll go through the status of hybrid power systems existing in practice, and then we have a case study here in Saudi Arabia in Rawdat bin Abbas, a village in the north near Rafah, for which we got load data and the site, and then what are the future directions. So, we have effect of increasing pollution and modification of the weather. We have natural disasters, and this is changing the climate, and we can say it's a human interference. And what is the result of this is falling buildings, freezing to that, and these are the things we usually see in the our news, printed media, electronic media, and this can be measured in terms of loss of lives, economic losses, and then we talk about the rebuilding. So again, it's a cost, and then overall is the inconvenience. These are some of the examples which you must have seen, but it's just refreshing to us. We have in Pakistan, and then Japan, tsunami, forest fires in Australia and other regions of the world. These are the consequences of weather modifications, which is happening because of our interference. This gives you an idea of how the weather catastrophes have taken place worldwide. See, so it is on the increase, It is increasing every year now and then till up to it's data for to 2013. And this is another example of disasters, and it's a burden in terms of prices, how much the nations and the people are paying. This is the effect of climate change, how it is changing. What are the ingredients which is causing these changes or modification in the weather? Global renewable energy scenario is as here stated. Net addition of 58.5% to global capacity in 2014. And wind, solar, PV, and hydropower dominated the market, comprised of 27.7% global power generating capacity, enough to supply for 22% of the global electricity. What is the solution for the problem I said, why renewables? We should use clean sources of energy. We should penetrate into our existing system and supplement, not replace, but supplement through these sources. And of course, the conservation is the most helping factor. We should, as an individual, work on it. The temperature, if we reduce for this hall, increase by, if it is now 15, if we increase by 1 degree Celsius, how much are we going to save? So each individual is work on this factor in houses, in offices. It will make a big impact on energy conservation. And we as individuals should take this message, we should work it out, and we should try to implement these as a moral responsibility. These are some numbers available on global energy indicators, and if you see, well, I cannot see it from here. Hydropower, renewable power, like in 2014, it reached around 657 gigawatt. So it's an increase every year. It shows that it is doable, it's achievable. The matter is how we take it. And these are some numbers, again, justifying the utilization of wind power resources and renewable sources of energy in the global scenario. And like wind power, if you see, it's been on an increase around 22%. What is the reason? What are we looking for? What we are waiting for? You know, so like I said in the beginning, we should take this to the end. You know, like wind resource assessment, everybody, because I am emphasizing this for the last 20 years in different meetings like this, that we have a hypothesis, you know, that wind resources are not sufficient in Saudi Arabia. This is general feeling. But this is not true. What we say is we say based on the PME data, which is the data, historical data collected at airports, 30 or 35 airports. And airports are the low windy sites. So we cannot take this as a reality, hypothesis, but we can start from there as we did 15 years back. So, I mean, we should think in this direction. And this is again the situation of wind power implementation in different continents. And like where are we? We can see here, it's very clear. Like we have wind resources on the other side of the Red Sea in Zafarana, Egypt. Why not we have on the other side of the, and I'm insisting on that to make the measurements. I have done a survey, you know, right from Tabuk till Jizan, Sporting, and I found some sources really the places are windy places, and that we submitted to Saudi Electricity Company some times back. And hybrid power system, now I come to the subject where it's a system like where you can supplement your existing system. There are around 41 villages in the Saudi Arabia which are not connected to the grid. Now, if we do the proper approach, take a proper approach, we can penetrate into it through certain percentage of wind and the total solar photovoltaic. And this is what we did a study for a village in Rafah, this Rawdat bin Abbas, you know, for Saudi Electricity Company. And as I said, the hybrid system are also being used worldwide. It's not again a very high tech or something not achievable, not doable. It is doable, and it's being used in many parts of the world, if you can see as listed here. And it's a just a line diagram of how the system works, you know. You take different system, you connect to the same bus, you know, through the inverter and converters, and it works, you know. And there are now the controls are available, which works really with the system, very friendly. And this is another diagram showing the, you know, the hybrid system, how it can be utilized and how it works, you know, in principle. There are some of the existing, you know, power plants, hybrid power plants rather I'll say, and they use vertical axis, horizontal axis, and PV and this combination, and it is, these are being used, you know. My emphasis is that they are being used. So hybrid power system, this is a case study, as I said, for a village here in Saudi Arabia. So what we did is we had the load data of the village, hourly load data for a particular year, and since at the village there was no wind data, so we took the wind data from the Rafa airport, and then we did this study, and we come up with a system which was feasible. 25% wind penetration was feasible in terms of technically, and whereas economics is concerned, if you take the international prices of the oil, it was compatible, but if you see the local prices, of course, it did not work. So what we did, we also, based on our preliminary study, what we did, we proposed to Saudi Electricity Company to conduct the wind measurement at the site itself, at their village. So we installed a tower, this 40-meter tall tower, and we put the sensors at 20, 30, and 40-meter height, 2 sensors each height, and then wind direction, and we also measured the pressure and temperature, relativity, and solar radiation at around 2-meter height. And we collected the data for 1 complete year, because in wind power sector it is said for a good study, you have to have a rule of thumb 1 year complete data for wind. So we did this measurement, and again it's not working.
It's just press just direct it to the ATV.
Here.
Yeah.
Okay. So we collected the data, and we found that at different height, you can see it's clear indication that wind increases with time. And also, diurnal cycle is there. Daytime, we need more energy and we have more wind. And similarly, during different months, summer month, we need more energy and we have more wind. It's proving. And this gives you the availability and the flow from where you are getting most of the wind. So in this case, at this village, we have most of the wind coming from northeast part and some from the south. And these are the frequency distribution that give you percentage of the time the wind is available and then the energy is available. So like 4 meter per second, around 70% of the times the wind is 4 meter per second, more than that. Means what? Your wind turbine can work at 3.5 meter per second. Usually the cut-in speed of the wind turbine is 3.5 meter per second. So you can have around 70% of the time, the wind speed more than 4 meter means you can have energy for that much of the time. So we use the wind turbine from DE Wind, and number of turbines and the rated power of those wind turbines. These are the specifications of the wind turbine, and we chosen for this study. And these are the specification of the existing power system at that village. And then these are some cost data, we assume, and some from the literature, because we don't have, if you say the wind turbine, okay, I know how much it will cost at the factory, but I don't know today how much it will cost in Rotherham Abbas, because traveling and transportation and all those. So these are some numbers taken from the literature, and we found that 25% penetration at this village is possible technically. And these are some results of this study, like how much cost is of the hybrid power system, and like diesel power system 28.5 halala per kilowatt hour, while the hybrid system was higher, 33.4 halala per kilowatt hour. So these are the certain findings of this study which we submitted to Saudi Electricity Company. And these are some of the recommendation, or you can say conclusions. As I said, that predominant wind direction was from north, and wind availability at 20, 30, and 40 meters at 4 meter per second was around 70%. And wind shear exponent, it's really very important, I did not mention before. A wind shear exponent, what tells you how the wind speed is increasing with the height, okay? And it's highly site dependent. That is why the reason why we make the wind measurement at different heights. Like you know, the wind speed at 20, 30, and 40 meters, with certain 90% confidence, you can say that at 70 meter height, this will be the wind speed, if you know your local wind shear exponent. And this is what wind shear exponent give you confidence. So this hybrid system, we recommended 25% and with a 33.3 halala per kilowatt hour. What are the future directions? Assess different hybrid system configuration to find a modular solution which could be applied to remote diesel generation. Like we can develop a map, and guidelines, stating 3 or 4 stations, doing some measurements, and then providing the guidelines that this is the village, this is the wind speed, and this is the distance from, so what type of system can be good for this village, for Y village, for that can be done, and it will be a guideline workable based on your, experimental findings. This is what I think we should lead towards now. And then do the measurement of, wind and solar and all those things. And then we can estimate the cost of implementation, real. And then, as I said, we can do the guidelines and also can develop a database which will be interactive. And this is what I had today. And I hope I was able to convey the message which I started with. This is an exercise, academic exercise. Beyond this, I wanted to give that message from this forum.
Thank you, Doctor. This is excellent presentation. The next presentation will be titled Brief Feasibility Study for Building a Pumped Storage Hydroelectric Plant in the Kingdom of Saudi Arabia. It will highlight one of the challenges facing the Saudi Arabia power sector is how to reduce the requirement and investment for new thermal peak plants in order to meet the rapidly increasing short-term peak demands. So the next presentation will provide an overview of a project. Its objective was to study the possibility of building a pumped storage hydroelectric power plants in Saudi Arabia. So the next speaker is the engineer Khalid Al-Soufi. He's from CAF UBM, from the research center. And Mr. Al-Soufi is supervising the high voltage lab and has actively managed and participated in many research projects related to the high voltage and power systems. And also, I would like to highlight here his active participation in designing and review the design for the lab and workshops for the National Power Academy. The floor is yours.
Thanks. Assalamu alaikum. Thanks, Chairman. يعطيكم العافية. شكرا for asking me to be in the presentation this stage. And thanks for the organizer and for the audience. The topic is this study. Really, it is done, sponsored by the Ministry of Water and Electricity sometimes before. And they were trying to raise or answer the question about the feasibility of building a pumped storage power plant and hydropower plant in the kingdom. Using the available capability, it was with concentration on using the salt water of the sea. And the main objective is to see how is it feasible. And then it is extended to use also the available water within the dams in the kingdom. As you know, generally, as a quick idea about pumped storage power plant, it has to have a top reserve and a bottom reserve where the water is passing between from top to bottom to generate power, and from bottom to top in order to raise the water again for gaining some energy which is going to be stored to store the electrical energy in such a mechanical form. Generally, the pumped storage power plant is one of the storage facility. We were talking about renewable energy through this morning as a whole, and there's many questions raised regarding the storage of the renewable energy in order to keep the continuity, and also it's a matter of storing the power to keep it as a source of, as a plant which is available for the kingdom. The beauty about this study to see if this is applicable to the kingdom, and you can see now, inshallah, it is applicable, and there is a big chance for that. This is the main feature, and internationally it's not unique. Pumped storage is an old, really, technology going no more than 50 years, and it's available in many countries in the world, as you can see. We have, in order to conduct this study, we have already used the listed methodology. We were trying to see, first of all, the available sites for using this type of technology, and secondly, we tried to see the power system for the kingdom, for the 4 sectors, if it is going feasible for them at some period of the year in the future, that it can supply this the requirement for this pumped storage, and it can consume the power required for that, and what is the best area for that. Fortunately, through the study, it was clear from the power system analysis and from all this studies that we have, it is conducted, and from the analysis of the system in the kingdom, with the future available for the system, that the best location is in the western area and the coast of the Red Sea. Part of this is to study the system as it is already seen here. It is already known for most of, for the electrical engineering, that this is the system in the kingdom, and this is the interconnection, which is already taken into consideration while making this study. And as we are going through the study, we realize that there is little shift in the, there is a little shift. It is realized that the peak is nearly for 2 difference, and here is the first peak, according to the hourly loading. And with this type of configuration for the power profile for the system, it is realized, and this is also the monthly system-wide load profile, which, as a model for understanding the system. So it was realized that according to the system capability and according to the future requirements, we need to we see that this water storage, generally, it depends upon the height, and as we see in the first picture, that raising the water up to the top reservoir, that means there is a height, and there is a distance between the lower reservoir and the top reservoir. There is a horizontal distance, and that's affecting all over the mechanism. We can see that for 1 giga, it is the red one, which is noticed through the whole study that it is the most feasible. That means the plant has to be about 1 giga. The system study conclusion, it has already proved there is 1 giga possibility of BSP, and that can work during 6 months of the year and can provide operating saving to the system. When we say operating saving to the system, you know, the prices it's for this pumped storage power plant in some other countries, they are selling. And one of the guys who was saying that in one time, those people who are producing nuclear energy, sometimes they have to, it is a base load, so it has to continue serving the system. And if you cannot consume it, then that's a problem. So those BSB, in some of the countries, they are really, sometimes they buy this power through a certain period of the day or the month in very cheap price and sell it when it is needed in higher price. That's for commercial use. Here we try to depend on the difference in the prices of the fuel, the utilization of fuel regarding the generating plants. From one area to one area, or from one time to one time, it's possible to use this incremental difference in order to make it feasible for the BSP. Okay. First of all, we have to try to find in the kingdom where is it possible, and in order to see that, we go through first in the Google and we try to search where is the heights available, which has to be close to the sea. For the sea BSP, as we said in the start, that we try to study the sea BSP served by seawater and also by drinking water or normal water, the rainwater which is coming from the dam. For the seawater, we have to be close from the sea. It was scanned from top nearly south of Aqaba up to the Jizan area. Through this green line, you can see within about 5 to 10 kilometers. And it was realized that the area close to Aqaba is the most prominent as the most feasible regarding PSP. As you can see, the main criteria, as we have already repeated, the location itself, geological and also environmental, in addition to the height, in addition to the location, proximity regarding the coast of the sea. All these are parameters. And there is one major figure normally when we see, okay, the distance, the height against the distance, or the distance against the height, the horizontal distance between the lower reservoir and the top reservoir, and then the height, it's maximum, it has to be 10, the ratio. Within that, it will be feasible. Above that, it will not be that much feasible. So we were searching within the 5 kilometer from the coast at Aqaba Red Sea there, and we find nearly about 10 sites which is somehow feasible, and the most feasible is which is cited here as site number 1. Then we try to make all the calculation, and you can see the characteristic of that and the main feature. Regarding this BSB and hydropower plant, there is a lot of construction there. There is a dam that you are going to build. Then you need to know the land, you need to know the availability of construction material, the availability of manpower. All these parameters has to come in the calculation in order to see if it is feasible or not, which is already included in the study, and it comes up with some good results regarding that. You can see the horizontal distance. You can see the top one, we need only one dam. If you need more dams and with higher size, with more height or more length, that means more cost. For this is for site number 1, it was the most feasible and with all the features there. So this is a pictorial type of view regarding the site in the north, which is close to, it's called, so this is the model for that site, and this is just to grasp the idea regarding the turbine. You know that part of that you need to build a huge tunnel, you need to build a huge area which is under the rocks or under the mountain, and there you are going to put a plant, you are going to put a pump. This pump, it has to be with a dual purpose. It can pump and it can generate. That's very special, but at the same time, as we were saying, that it's an already known technology. It is feasible for this 250 megawatt turbine. There was, so it's expected to be 4, and this is just only to see how is the sizes and the dimension of the turbine that's expected to be in this site. And maybe there is a human being somewhere. There is a human being somewhere, and you can see how is the height, how much excavation that it's needed for that, and what's the civil construction for that. So that's for the sea, but for the fresh, also it was really a big question. Where is the rivers in Saudi? Then the people who were raising the question, where can you find the water? And really, it was a fantastic thing that we find a lot of dams in the kingdom, and one of the major dams is called Beish. It's in the south, close to Jizan. And that site, really, it was a very huge lake, which holds about 190 million ton of water, million cubic meter there. Not all over the year, it goes ups and downs, but with the minimum, it can reach about 130 million meter cubic there. So, and luckily, it was found a suitable area, suitable topography at that area where you can utilize this water to raise it up and get it down within the formula that we have said about 10. طبعا وادي بيش, in order to study the subject you need to return back to the water flow and rain and also the what do you call it, the water, how it's evaporate, in order to replace that one. So there's a dam there which is called Besh Dam, and you can see the picture of that one. It's very huge really, and it's hold a lot of water, and this is the area there, and this is the expected site on the top, with the topography there about 350 meter the difference in height, and with the distance. But the water needed there, with respect to the one in the sea, it's about 5 million cubic meter. You need to bump it up and make it down, while for this is about 12 million meter cubic. One thing to be noted here, that the water is not going to be consumed. It's rotating within a closed cycle nearly. It's only the evaporation. Regarding the evaporation, that's the things that you are going to cover up, and so that the water will be conserved. It's not the water will be somehow waste some, but you are utilizing this. This is the quick economic analysis of this one, and it can show that what's called Magna site, which is in the north of, for the seawater utilization, it has a benefit to cost ratio with a 1.31 as an index, that net present value and also payback period there is cited, which is mostly for all the options about 11 to 12 years, which is a reasonable number. For Magna site, we said there is Magna 1 and Magna A and Magna B. As you know, for the seawater, it's a salty water, and salty water by itself is a big problem regarding the corrosion. So there is another option, which is to make a small desalination plant in the Magna site, where you can cover up the evaporation, and that's also included in the calculation, and it comes up better with respect to the feasibility. While for Besh, as you can see, also it has a very good profit to cost ratio and return back. It is generally feasible. So the conclusion for that, as you can see, generally it's feasible. It's a 1 gigawatt for pumps for turbines. And also the sites in Magna, there's two options for that, one for desalinated water and one for salt water. And for Wadi Besh, which is in the south, it's also feasible. And I'm sure that this whole study now in the hand of SIC, it was done for the Ministry of Water and Electricity, but now it's handed to the Saudi Electricity Company, and maybe under further study in order to see how to go ahead and implement it. Thank you.
Thank you, Doctor. The next presentation is titled Leading Experience of Korean Nuclear Energy by the Dozan Company, and it will highlight the Korean experience and the power shortage after the Second World War and the Korean War, and the Korean government, how they decided to introduce nuclear power as a major source for the power generation. The presentation will be delivered by Mr. Kang-gon Lee. He's the Senior Manager, Nuclear Power Equipment Technical Marketing from Dozan Heavy Industries and Construction. Let's join us.
Assalamu alaikum. How about my pronunciation? Is it good? Thank you very much. Nice to meet you. I'm Kang Hyun Lee, working for Doosan Heavy Industry in Korea. I'm very honored to speak in front of a distinguished engineer from Saudi Electricity Company. Today, I'd like to share our manufacturing technology and localization experience for nuclear equipment. Yes, my presentation will be divided into 4 parts. Firstly, let me touch the benefits of nuclear power in Korea, and then I will explain about the manufacturing of nuclear equipment, especially for nuclear steam supply systems. And thirdly, I'd like to share our localization experience. And lastly, I would like to propose the cooperation plan for equipment localization in Kingdom of Saudi Arabia. Before going into details on manufacturing and localizations, let me briefly highlight the benefits of nuclear power in Korea. After Korean War, Korea struggled with a severe power shortage, as you know very well. For this reason, Korean government has to decide to introduce nuclear power as a major source of energy. Thanks to the stable supply by nuclear power that was considered to be the most affordable energy, Korea industry was able to achieve constant economic growth. According to the data from World Nuclear Associations, nuclear power is the cheapest source of energy. In case of Korea, for the last 30 years, consumer price raised 270%, but electricity price raised only 23%. This was the driving force of a Korean economy. Currently, nuclear power is 30% of total power generation in Korea and is in charge of a base load of electricity supply. Now, 24 units of nuclear power plant are operating and 4 units of nuclear power plant are constructions. Thanks to the continuous construction of a nuclear power plant, we have a very competitive construction cost comparing to other countries. We are building nuclear power plant, 4 units of nuclear power plant in United Arab Emirates. In the next chapter, I will explain about the manufacturing of nuclear equipment. Yes, this is a typical contract structure of a nuclear power plant project in Korea. Doosan is responsible for supplying nuclear steam supply system and turbine generator system. This is a bird's eye view of nuclear APR 1400 nuclear power plant model. APR stands for Advanced Power Reactor. The electrical power output is 1,440 megawatts, and the design life is 60 years. The fuel cycle length is 18 months. The number of coolant loops has 2. In the nuclear power plant, the center of the nuclear power plant, we call it a nuclear steam supply system. Nuclear steam supply system is the most important part of the nuclear power plant. It consists of 1 reactor vessel, 2 steam generator, and 4 reactor coolant pumps, and 1 pressurizer. Yes, this is technical data of a reactor vessel for APR 1400. Reactor vessel consists of a head and vessels. Head has 103 closed head nozzle on top of the head. And vessel has 2 outlet nozzle and 4 inlet nozzle and 4 direct vessel injection nozzle. The overall height is 14.8 meters, inside diameter is 4.6 meters, and dry weight ton is 525 tons. Yes, this is technical data of a steam generator. Steam generator consists of upper head, upper shell, lower shell, and primary head. In the upper shell, there are steam separator and dryer for steam evaporations. In the lower shell, there are 13,102 tubes for heat exchange between primary side and secondary side. The overall height is 23.1 meters, inside diameter is 5.9 meters, and dry weight ton is 780 tons. Yes, this is a manufacturing flow of reactor vessels. Reactor vessel is made from dome and shell-shaped heavy forging materials, which are assembled to 3 parts. The role of a reactor vessel is to contaminate coolant within the systems and control heat energy generated from nuclear reactions. The total manufacturing process takes 48 months. No, sorry. This is a manufacturing process of a steam generator. Steam generator also made from dome and shell-shaped forging materials. The role of a steam generator is to convert heat energy generated from reactor vessels to kinetic energy by generating steams, which will be carried out to turbine generators, which will produce electrical energies. The manufacturing of a steam generator takes approximately 54 months. Next, let me touch our localization experience for nuclear equipment. This is a history of a nuclear power plant project in Korea. Prior to Yeonggwang 3 and 4 project, Doosan partially involved in manufacturing nuclear equipment. After Yeonggwang 3 and 4 project, Korean government initiated localization program, and Doosan was selected as a main contract for nuclear steam supply systems. Doosan's localization was achieved by 3 phases. In the localization phase, technical transfer program was carried out for the period of 10 years, starting from 1987 to 1997. Technical transfer program include design, manufacturing, and project management. Many Doosan's engineers were dispatched to licenses place to run the technology, and license dispatched each engineer to Doosan shop for technical consulting. Yeah, during the period of 2007 to 2011, we transferred our manufacturing technology to 7 Chinese companies. The method of technical transfer was almost the same, what we have received before. There are several factors for successful equipment localization in Korea. I think the most important thing is government's strong commitment and support. And then next is step-by-step approach with a long-term program. We have been achieved for the period of 10 years. Lastly, I'd like to propose cooperation plan for equipment localization in Kingdom of Saudi Arabia. For the successful localization, I recommend step-by-step approach with a long-term plan is required. For the first step, it should be led primarily by foreign country. Partial participation of local company. But at the second step, with the assistance from the foreign company, local company increase the participation of localizations. And last step, at the final step, most work can be done by local companies. We will provide support as deemed necessary. This diagram shows the detailed process of equipment localizations.
Excuse me, 3 minutes more.
Huh?
3 minutes.
3 minutes.
Left.
Before starting actual manufacturing, local companies should prepare required documents for QA systems and qualified personnel through on-the-job training and on-the-job participations, and appropriate equipment facilities. If required mock-up test, we will support local companies. And also we will provide technical consulting to documentations, productions, testing, and code stampings. After completion of one cycle of shown on the diagrams, the capability of local companies will be increased enormously, and the Doosan support will be gradually decreased. Yeah, for the successful localization, we will provide technical transfer programs, including document for actual manufacturing. We also provide building of new factories or upgrade manufacturing facility for equipment manufacturing of nuclear power plant. The picture on the right side are the aerial view of Doosan manufacturing complex and our nuclear shop. Yes, in order to manufacture nuclear equipment, getting ASME stamp is mandatory requirement, and QA system properly established. Doosan will provide support to improve and establish QA system for your local companies. Yeah, this is the end of my presentation. I think I already surveyed several companies in the eastern area of Saudi Arabia in Dammam. I think the Kingdom of Saudi Arabia's industry have a better resource, especially human resource and infrastructures, compared to when it started a localization program in the early 1980s. If Kingdom of Saudi Arabia's nuclear program starts, Doosan will do our best for Kingdom of Saudi Arabia with our experience and technology. Thank you very much. Shukran.
Thank you, Mr. Kajkumli, for excellent presentation and sharing the experience. The last one in our session today, presentation titled Nuclear Energy and its Safe Use. And it will highlight the safety issues of using nuclear reactors to produce power. And it will be presented by Dr. Ali Elmar, PhD in Physics, Radiation and Environmental Protection, and Master degree in Nuclear Engineering. He is the founder and premier director of the Nuclear Energy, Radiation Protection and Uranium activities in Jordan in the period from 1980 to 2008. He's also worked as a senior advisor for the Minister of Energy and Mineral Resources from the 1997 to 2008. So let's please go ahead.
بسم الله الرحمن الرحيم الحمد لله والصلاة والسلام على رسول الله وسلام على ساكن هذه المدينة الذي أرسى حقيقة أسس الحضارة البشرية المعاصرة التي نجتمع اليوم على هامشها. أشكر الأخ رئيس الجلسة وأشكر جميع الإخوة الحضور على هذه الفرصة الطيبة. هذا العرض يعني اللي اوت تبعت المحاضرة. Sorry, this is the layout of the lecture. So we will talk about 7 points: nuclear power, nuclear safety, safety designs, monitoring safety features, nuclear accidents, lessons learned from nuclear accidents, and then the conclusion. Nuclear power started in the mid-50s with a reactor in the last Soviet Union, 5 megawatt reactor. And it progressed very fast in the 60s and 70s, and then started to retard in the 80s of the last century because of the Chernobyl accident, until we reached the Fukushima accident, where they retarded too much. Anyhow, the energy produced 70 terawatt hour in the last period, and experience we have got about 1,500 reactor year. This is as regard to the power stations. In the year 2015, there were 438 nuclear power plants or reactors with 379 gigawatt in operation and about 67 nuclear power reactors under construction. Nuclear energy is used in civilian activities, and it is too much spread in medicine, agriculture, water, scientific research, etc. All fields of the life, we use nuclear energy in those fields. And it is used in military, as you know, the case. The threats, we have uses and there are threats. So the threats, accidents, and wars, and ill well activities. Now we have some illustrations. In this diagram, the atom splits into 2 fragments when bombarded by a neutron. So 2 fragments, 2 nuclei of lighter elements. And then we produce also 2 neutrons, 2 to 3 neutrons. These 2 to 3 neutrons can be used to produce new fissions, and the situation or the process continues in a very fast manner, and we got a very huge amount of energy in very due time. This is the chain reaction, and that is the nuclear power station. Here is the reactor in this, the left side. the containment structure, the reactor vessel, and in the middle of the reactor vessel there is a nuclear core or the fuel which we generate power in, and you see it is just a boiler. Nuclear reactor is just a boiler, similar to other boiler, but the energy is produced from nuclear fissions. And the other part of the station is similar to conventional power plants. We are also concerned with the nuclear fuel cycle. Here from this, from the land, we take the uranium ore and we process it until we use it in the reactor, and we dispose it into the ground as a waste material. Nuclear safety. Now we are talking about nuclear safety. There are three topics or subjects which we are concerned in. These are the security and the safeguard, and this I add the third one, the supply and use. This is not found in the literature, but for a third world countries or for a developing country, it is a concern. It is a big concern. It is not matter to have the reactor itself, but it is matter to maintain the reactor and to operate it and to keep it functioning. Otherwise, it may become something harmful or may lead to accidents. So the security, intelligent planning, a proper design, well-developed safety culture, contingency preparation for the accidents, and the safeguard, know-how, not to spread the know-how for those who are going to make nuclear weapons and so on, knowledge and design, requirement, materials and requirement, ready-made devices. You can get a nuclear bomb from the market, from the black market also. This is the third one, even if it is very unsecure. Supply and use, industry and infrastructure, human resources, and finance. As I told, this is the most important for the third world countries or for the developing countries, is to keep the reactor operating in a good shape and good manner. Safe design, this is one point of the fifth. Safety systems, active systems and passive systems. The active systems using electricity and mechanical parts to control the reactor or the power station activities or working. The passive system, this is worked alone. Industrial pressure relief valves, if the water heated too much, then there is a relief valves which can reduce the energy or the heat in order not to damage the fuel rods. Physical, such as gravity, this is working to, for example, to shut down the reactor, the control rods, to make them drop into the reactor core, so it will be shut down if some heat is generated too much. And heat convection, resistance to temperature, the systems or the devices or the materials used should be resistant to high temperature, resistant to radiation, and resistance to chemicals. So these are the safety systems. Now, the safety features, this includes the containment integrity, control of reactivity, fuel cooling, inherent safety, and contain the radioactive materials, fuel, will waste, will leaks. So to concentrate for the safe design, we consider these subjects in any reactor or power station case. Monitoring function of safety features. Safety systems, active systems, electrical or mechanical, or pneumatic, and passive systems, industrial pressure, etc., relief valves, etc. Oh, sorry. And, monitoring, containment structure integrity. This can be monitored by periodic measurements of leaks in air, and even by visual monitoring if some cracks or some deficiencies occur. Fuel pellets by examining the physical characteristics, shape of the and conductivity. So the fuel, if superheated, then it bent or damaged, you can monitor it by this case. Fuel cladding by measuring the amounts of radioactivity in cooling water. The cooling systems by measuring a rate of leak of water, and the core heat by measuring water heat, operational and radioactive decay. This is the radioactive decay. It continues, the reactor core continued to give heat even after 1 week or more, and it is a big amount, about 1 in 1,000 of the power, heat power, can be generated. So we need to take care of this situation in order to keep the reactor safe. Nuclear accidents, a definition, and events led to significant consequences due to heat rise, water or radiation leaks, damage, explosion, etc. It causes either industrial, man causes, or natural disasters. The statistics up to 2011, about 400 accidents, major accidents, or to some extent, and 36 fatalities. These are those who died in these accidents, and 1,680 injuries. This is in the world. This is the scale of the accidents in the international accident scales. It is divided into 7. Yes, 7. The most one is that one. It is at number 7, major accident. It is a logarithmic scale. This is the idea which we should understand. That is, it is a logarithmic scale. Every stage is more than the other in a manner of logarithms. In major nuclear accidents, as we know, 3 Mile Island in the USA, the Fukushima in Japan, and these are some statistics about these accidents. This is the continued the Chernobyl accident. Okay, then the lessons from nuclear accidents. Inner design. After every accident, all the world is concerned, and they are developing new designs and ideas and legislations, or like so. So the inner designs, full fuel in the form of solid ceramic pellets. It gives a good design. Or pellets are packed in sealed zirconium alloy. Fuel rods are confined inside a large steel pressure. Supplementary inner safety systems. These are the areas which the humanity or the people over the world develop their designs and nuclear reactors to prevent more accidents. Lessons learned: the outdoor physical barriers, they make more effort.
Be close to the, yes. Be close to the mic, please.
Sorry. They are making sieges, security checkpoints, flood dikes to prevent water, wind barriers, defense requirements. These developed very well after the accidents. Water supply, unlimited, a river or a sea. So we cannot, in Jordan, for example, we cannot claim that we are going to nuclear power since we don't have the water. But here in the Saudi Arabia, you have plenty of water and seas, so it is not a problem to have water supply. Gravity driven coolant water. Yes, these are from the lessons which we extract from the accidents. Continued, soil and land. Soil should be stable, physical and chemical fitness, less liable to earth movement, less prosperity, international cooperation, standardization of designs, harmonization of regulations, human resources development, exchange of experience, advising on disaster relief, and codes and regulations. So these are every accident. We go through all these and modify until we get very safe designs. Conclusion, nuclear power plants accidents, chances of occurrence. It is in new design very low. It is about 1 to 10 millions or even to 100 millions. These are in respect to designs. But the situation is different. It is not only the design factor which make the accidents, but practical it is 1 to 1,500 per reactor year. More year reactors, more frequent accidents. So if we plan to have, for example, 4 reactors, then we should multiply this factor by 4, or 5, we should multiply it by 5. If we will operate it in 100 years, you should multiply in 100 years. So the final figure we get is the probability of having an accident, a real accident in this situation. Nuclear power is safe, let us conclude, safe and reliable, but costly and risky. What determines to go nuclear or not? 3 principles in international principle. These are the justification. The first one is the justification. Is it justified to go nuclear or not? If we have other alternatives, we shouldn't go nuclear with less prices, etc. Optimization. This is related to the radiation protection situation. We have to pay money for the optimization. We have to calculate all the costs and to compare it or to include it into the feasibility study. Those limitations, although we have done the first 2, we must also keep the doses, the radiation doses, under certain levels which are acceptable or said to be acceptable in the standards for radiation protection. Thank you.
Thank you, Dr. Ali. And we reach now to the last part of the session, to the questions. And please allow me, before we go to the question, to summarize these 4 technical papers. The first one was about the wind energy for remote village. It was presented by Dr. Shafigar, and he discussed one feasibility study in one of the villages in Saudi Arabia. The second presentation was about the hydro plants in Saudi Arabia, and also it was discussed through a feasibility study by engineer Khalid Soufi. And the third one was the experience by the company Dozan from the Korean related to the nuclear energy by Mr. Kag-Hun Lee. And the last one was by Dr. Ali. He highlighted critical issue related to the safety when you are using the nuclear. So again, now we'll take the questions, and please, before you raise your question, mention your name and the company as well. Go ahead, please. Go ahead.
I am Abdullah Al-Amri from Saudi Electricity Company. My question to wind turbine. Before 8 years, there was a summit for GE at the Doha, and there was a paper there, and they mentioned most of the land of Saudi Arabia meet the minimum requirement to install wind turbine. In your presentation, you said that you collect data from different airports, or mostly all airports in Saudi Arabia, and give a potential to install wind turbine. In different occasions, we heard that from many responsible people. They said that we have only minimum areas or location that meet the minimum requirement to install wind turbine. Your comments, please. This is for you. And for the question for Mr. Dr. Ali, that you said it is safe and risky. How it comes? Thank you very much.
Go ahead.
Thank you very much. That's a nice concern. As I mentioned in my presentation that this is a myth, you know, we don't have wind in Saudi Arabia, potential. But we do have windy areas in Saudi Arabia, and that has been identified based on the airport and then verified further with the measurements at up to 40-meter heights. And now presently we have around 7 stations which are measuring wind speed up to 92.5 meters above the ground level, and we are getting like at 80 and above more than 7 meters per second wind speed annual average, which means it's like in Aqaba region. So this is proving that we have a lot of potential in Saudi Arabia whereas wind is concerned. The only thing is, like in eastern region, the Haran is the potential area, but if you go around, you don't find the, you know, land, which is, you know, you need a lot of land for that, which we don't have it. Like, but if you go to Dulam, yes, you have flat land, very good for wind power generation, where we have good wind annual average over there. Yambo area, RR, and this northern area is all good. I mean, good means excellent for wind power generation. There's a lot of space available there. We can go for multi-megawatt, means 100, 150, 500 megawatt power plants using wind. And there is also, the next thing is the connectivity, the grid, and the grid is available in all of those areas. I hope I answer your...
Dr. Ali?
Yes.
Yeah.
Yes, nuclear energy is safe in respect to design. If we speak about design of nuclear reactors, it is very safe. The probability of having an accident due to malfunctioning of design is 1 to 10 millions or even to 100 millions per reactor per year. It's very, very, very small. But the situation is not this. Many factors affecting this situation. How we can operate it? Are we organized well? Do we have these materials well? Okay. How we operate it? So according to the practice, the accidents probability is about 1 to 1,500 per reactor year. So to reduce too much from 1 to 100 million to 1 to 1,500 per reactor per year, too much gap. Then the other thing, suppose we have 5 reactors, like Saudi Arabia is going to establish 4 reactors and Jordan 4 reactors, etc. You should multiply this figure by 4 or by 5. So it becomes 1 to 300. The probability is 1 to 300 per year, 1 to 300 per year. And suppose in a 100-year operation, then it becomes 1 to 3. The probability is 1 to 3. It is a big probability to have an accident within 100 years in 5 reactors. Now, the risk or the detriment occurs due to nuclear reactors, even if it is psychological, but there is a risk, and it is very big. You have to pay money. You have to evacuate areas. You have to spend time in recruiting the situation. So it is risky. This is why we see it is risky, but it is safe in design. In practice, it is risky to these results.
Okay, thank you, Dr. Ali. Any other question, please? Still we have time, so go ahead.
السلام عليكم.
عليكم السلام.
عدنان الأحمدي, Medina College of Technology. The first, I have two questions. The first question to Mr. Shafiq. From your experience, what do you think about geothermal? What's the potential of geothermal energy? Which I think many studies show that geothermal is the second source after solar energy in Saudi Arabia. The second question to Professor Ali. As I reading from the Fukushima accident, that the main reason is the water pump circulating, which is, if you ask anybody, it's expected to get a failure for any circulating pump. So, any precautions if, for example, the circulating pump for cooling get failure or something? Thank you.
Yeah, thanks. As you said, geothermal sources are really, one of the potential area in Saudi Arabia. We have a lot of geysers, and we have Harat, in the western region. And back in 2005, I presented this first study on geothermal sources as power generation in Turkey, Istanbul, on the International Geothermal Congress. And as of today, to my knowledge, we have not assessed the resources, like the lifespan of the resources and the technical feasibility of harnessing geothermal resources into being. Some of the work is going on now at King Saud University, Riyadh. They are doing some like drilling and all those things to assess the resources, basically, of Harat, So it is a promising source. It is available. It is there beneath your, and the matter is to make the assessment first thing, and then utilize it. So I think Kingdom is moving towards that, and what the academicians need, the resources, the fundings from the power utilities or the government, that is what our hindrance I am seeing into the slow development in this area.
Okay. Dr. Ali,
yes.
Second part.
That's a good question. Yes. As we mentioned in the lecture, we have active and passive systems for safety. In the cooling system, there must be good quality pumps. This is one thing. The other thing, there should be standby pumps and network and systems so as to switch on in case of accidents or failure, etc. The third one, which is also very important, is to have the passive features in your designs. The passive features, for example, if you can have water coolant flow through gravity in case of accidents also, it will be much better than to have just rely on your mechanical or electrical systems.
Okay, just to complement your answer, I think the risk is there in any operation. However, we have to look into the control measurement that will eliminate as possible. There is always a percentage where we can see the failure. However, in the nuclear is very dangerous, so always we have that as measurement control for any failure. So now we'll take another question. Go ahead in the middle.
I have one question actually concerning the cost of the installation of a nuclear reactor. I didn't see in the presentation how much it will cost the nuclear reactor plant and how much the cost of the energy coming from this plant. Second, concerning the highlight points of Dr. Ali, is that it's safe but risky, reliable and costly. So we are playing with 50-50%. We have a wisdom word saying that if it's 50-50, don't play around with it unless you are sure that it is safe enough. So in my opinion, that I didn't see anything that how much it will cost the energy production from these nuclear reactors.
Okay, thank you.
Yes, thank you very much.
Thank you. Go ahead.
Okay. Thank you. The cost depends on local situations more also. Yes, you can buy a reactor, but it is, the nuclear power plant is not only the reactor. It depends on the cost of the money. It depends on the spare parts which you can make locally or not. It depends on the companies which you are going to hire. They are costly or not. But we can speak of 10,000 to 20,000 or even more 10 to $20 per watt, or 10 to 20,000 dollars per kilowatt. This is the capital cost for a nuclear power plant, and even you can get it with more cost than this. In some situations, like the Bushehr power station in Iran, it costs a lot. In Pakistan, because they were besieged, and they established the nuclear power in Karachi, and then they stopped supplying the fuel from abroad. So it becomes a little bit costly, and they didn't operate it on full scale. So it depends on the local situation rather than the reactor cost itself. The reactor cost is not the only major factor affecting the cost. As regards the power production, also it depends on the local situations, but we can speak of in some 7 cents per kilowatt hour in the US, 5 to 7 cents per kilowatt hour. But in the developing world, you have to think of more cost than this, even 3 times or 4 times, because of the uncertainty in the operation and financing and maintaining the nuclear power plants. This is one thing. Again, I want to stress that point. The safe and risky. Yes, it is safe and it is risky. It is safe in design, but it is risky in operation. And this is the world experience. It is not a judgment. As I told you before, the probability of the likelihood of having an accident is 1 to 10 million or 1 to 100 million if it is if the design is considered only. So it is safe from the design side, but operation and maintaining and the skills. And yes, and there are also many other factors which you are not considering. For example, the earthquakes, the wars, and these things make the reactors risky. Why are we said risky? Because of the expected fear and the expected damage, the large expected damage of such a technology. This is why we said risky. It is the expected damage. It is very huge. The people look to it. It's very huge damage, like Fukushima and Chernobyl. If this accident occurs in a similar size power station, conventional or solar, you will not speak about risk or risky. You know, what accident you expect from a solar system? You cannot expect it. We have to differentiate between risky and safe. Is it clear?
Yeah, I would like to ask about uranium enrichment. Why we don't learn lessons from our neighbors? You see what's happened to Iran? They can't do uranium enrichment. They are begging Russia for the uranium enrichment while they are so advanced in nuclear energy. Also, what's happened to Iraq when they have erected a nuclear reactor and they couldn't run it, and it costed $3 billion. So I think so to learn lessons from the others is very much
more important for us than to proceed and to think what we should do.
Yes, this is right, yeah.
Yeah.
Okay, thank you, Dr. Ali. I suggest you next time to change the slide to make it just risky, so to avoid the confusion. I think we have only room for one. Go ahead. Do you have any?
Yeah, I have a question to Saudi Electricity Company. I heard the Kingdom of Saudi Arabia has a huge plan to build a nuclear power plant up to about 17.8 gigawatt up to 2030. Is that correct?
If we just leave this message in the end, I think we have the expert and those who are leading this initiative. So I will leave it after the session to take some discussion with the specialized people. Follow me. So if there is no question, I have the last question. Go ahead.
Assalamu alaikum. Thank you for all speakers. My question to Dr. Ali. Are there any waste that produced from the nuclear power plants? Any waste? Or how can we manage if there are any waste? How can we manage that or store this waste? Thank you very much.
To whom this question you want to answer?
Dr. Ali.
Dr. Ali.
Yes. Bismillah. Now, yes, we have a lot of waste from the nuclear power plants, and they are classified into 3 categories: high-level waste, and medium-level waste, and low-level waste. This is from the reactivity point of view. And we have also classified into solid waste, liquid waste, and gaseous waste. Now, every type of waste should have treated into a different way almost. The high-level waste should be confined in cement, قوالب cement يعني بالمعنى هذا, or glass, and then buried into the ground. The others should be kept for some time in the site until the reactivity is declined. يعني تنحدر مع الزمن الإشعاع until the reactivity is declined, and then they processed it and also cemented it or glassified it and sent it to the barriers underground also. The gaseous, they keep it into the site for some time until the activity is declined, and then they release it into the air. When the activity becomes, let me say, safe, even though there is no safe, but according to the accepted levels in the country, in the concerned country, then they spread it into the air after dilution and confinement, etc.
Okay, by this we reach to the conclusion, and before we close, I would like to thank you and thank our speakers for the active listening and participation. It was last session. I know it is not easy to keep everybody excited, yet they were able to enrich the discussion. So thank you very much.
بودي هنا أشكر طبعا المهندس أحمد العيسى رئيس على إدارته المتميزة لهذه الجلسة، اللي يمكن محاورها بتتوافق مع مشروع الأكاديمية الوطنية للطاقة، لأنه في بعض التخصصات اللي حيتم التدريب عليها النيوكلير تكنيشن والرينوبل انرجي. عن مدير إدارة التدريب وجميع أعضاء اللجنة المنظمة، ودي أن أشكركم على وجودكم معنا خلال يومي الملتقى اللي سعدنا بوجودكم، ونتمنى إن شاء الله أن نكون وفقنا في خلال اليومين هذه إنه قدمنا لكم أوراق عمل تتوافق مع توجهاتكم وتحقق تطلعاتكم، لأنكم بالنسبة لنا عملاء غاليين ونسعى لهذا الشيء. طبعا خلال الملتقى هذا قدم حوالي 19 ورقة عمل، قدمها أكثر من حوالي 20 متقدم. في محاور اللي هو كفاءة الطاقة والطاقة المتجددة والطاقة النووية. الحضور بلغ حوالي 400 مشارك، وهذا الشيء يسعدنا، لأنه إحنا بداية الملتقى بدأنا من قاعة صغيرة، كان الملتقى الأول وقدم في فندق الميريديان، عبارة عن قاعة صغيرة أخذناها، عدد المشاركين ما تجاوز 160، واليوم الحمد لله وصلنا إلى 400 مشارك. فإن شاء الله نعدكم خلال الملتقيات القادمة إن حنكون عند حسن ظنكم، وحنسعى إنه نبحث عن كل المواضيع اللي تهمكم كمهندسين في الشركة السعودية للكهرباء. طبعا ما يفوتني هنا إنه أنا أشكر جميع الإدارات اللي ساعدتنا، على رأسها إدارة كهرباء المدينة، على كل الدعم والتيسير اللي سهلوا لنا إياه هنا، وشعرنا كأنه نحن في جدة، ما نقص علينا أي شيء، كل الإمكانيات واللوجستيك اللي إحنا نبغاها وفروها. طبعا نشكر إدارة مشاريع التوليد، إدارة النقليات، إدارة تقنية المعلومات، الأمن الصناعي، جميع الجهود اللي في الإدارة اتكاتفت لإنجاح الملتقى هذا، فلهم الشكر والتقدير، ولكم الشكر والتقدير على مشاركتكم. طبعا حيكون الرابط زي ما هو واضح عليه أمامكم في الشاشة، جميع الاستفسارات أو التعليقات أو الفيدباك ترسل على هذا الرابط، وإن شاء الله حناخذها في عين اعتبارنا. طبعا أحب أذكر مرة ثانية إنه جميع أوراق العمل، الفيديوهات اللي عرضت كلها حتوضع على رابط للمشاركة، وحترسل لجميع المسجلين اللي شاركوا معنا سواء من داخل الشركة أو خارج الشركة. فجزاكم الله خير، ونشوفكم إن شاء الله في الملتقى الخامس بإذن الله. جزاكم الله خير.
شكرا مهندس أحمد. أيضا ندعوك لتكريم المتحدثين في هذه الجلسة.
مهندس جمال طه. نسيت تقول مكة، شكلك ما تدري. لا ما حبيت ارتبط بواحد. لا تنسى تقول لهم على السلامة. طيب خلاص نرجع على لا بس نصلي وبعد
أيضا ندعو مدير كهرباء المدينة المهندس جمال طه لتكريم المهندس أحمد العيسى. شكرا جزيلا لكم وشكرا لحضوركم. وجبة الغداء ستكون إن شاء الله بعد الصلاة مباشرة. شكرا لكم.
يعطيك العافية يا أبو عمر. يعطيك الف عافية يا رب.